right now. So so the talk and the meeting is being recorded, and if you would rather not be recorded, then just turn your camera off and use the chat to ask questions. So we will take questions after each talk, and you can either put them in the chat or just raise your hand and ask them directly. So this is the last day of this Newton Institute workshop on verified software tools and experiments. But we have some celebrities talking today, and so the first one is. I need to dismiss some windows here. So our first speaker is Lenore Zuck from the University of Illinois at Chicago. And well, I'm not sure she needs much of an introduction. Well, certainly I was, in my own work on compiler verification, I was greatly inspired by her work on translation validation and the TVOC system. But she's done a lot of other kind of work in software verification. And so today she's going to advocate for a teaspoon of formal methods instead of maybe a full cup or two. Thank you, Lenore.
Thank you. What a wonderful introduction. I should nominate to be my introducer. So Shankar's mandate for the talk was, at least to me, addressing the challenges of creating robust, scalable, and usable tools and a tool infrastructure for the analysis, verification, and synthesis of software. Of course, I couldn't do it all, and each of us took whatever we wanted. I wanted to focus a bit more of what scalable means to me, and what does it take to create usable tools and for analysis and verification, and I'm talking small v verification, not a big full verification, which I think is what we need in lots of things. So where do I come from? Oh, I forgot. I come from Lincoln Park. And since Nate gave pictures yesterday, I want to compete with him. But then my dog heard that this talk is recorded and she said she's got to be part of something because she's just been editing things. So here she is in the Lily Pond in Lincoln Park. So for me, the notion of scalable is more about the science of using science. How to make optimal use of what we know or the tools we have in our discipline. So we talk a lot about scaling in size. We do that a lot. We do a really good job. We go from 100 variables to 100,000 variables. But I think we need also to focus on scaling in the target of applications to find larger markets and settings for the things we do. And I'm going to give 2 examples of things I have been involved with that are along this line, and what at least from this very narrow standpoint, what were my conclusions? So I'm going to start with translation validation. And the vision was from Emil Noeli that he was involved in some European project. And they wanted, and SNECMA wanted to make sure that everything is fully verified. And there was an issue of translating from Ada into, I don't remember the name of the language. And they wanted to verify the translators. His insight was that validating the translator is verifying the translator is a very big job. Moreover, once you validate a translator, you need to freeze it. So instead, we can verify each run of the translator. The advantages would be that you can continue developing the translator. It's going to be cheap. And it also would provide for independent cross-checks. Of course, the disadvantage is that will be additional cost for each one. But as experience has taught us, it's not a lot. It's well worth it. In the very high level, we have a source, let's say S, a target, say T, and great names. And we assume that they're both in a language that we can create semantics mapping. So we will be working on the semantics of S and the semantics of T. And to show that T is really a good translation of S, we create a refinement mapping such that everything that T produces can be produced by S. And this is the general idea of translation validation in its various forms. It's been mainly applied to optimizing compilers. They're trying to go very high level, more or less the recipe to do that is that you express the source and the target as a control flow graph. You find a cut set point that is a set of points in both source or target that includes the initial location, the termination location, assume one termination, and includes at least one node from each loop. So then you create a data mapping that kind of looks like under certain conditions, this variable of the source is expression of the variables of the target. You create control mapping from those points you selected in the target to the points you selected in the source. I put it in a different color, which happens to be red, no meaning to the red, generating variance for each basic block. And the reason that I colored it, sometimes it's done and sometimes it isn't. And you identify verification condition for each simple target path. That is a path between two of those selected target nodes that doesn't pass any other. Then you validate the verification condition using SMT solvers. So if you do include the invariance, you just get more power for some non-structure preserving transformation. Later, there was a need for some meta rules, for example, for loop optimizations that depend on affine transformation. And as Kedar and I later found out, for interprocedural optimization, it really helps to have meta rules. So you can have a bunch of stuff on the side. And we have, with Kedar, a more contemporary version where we annotate the optimization and generate witnesses, and we have a new idea of shadowing, and all this makes this verification conditions, their generation and their checking simpler. It's all small variants on the same theme. But the real work is in static analysis, which is, I consider, extremely light formal methods. The framework itself is where you have more formal methods, and the framework itself is very sensitive. Even the shape of the verification conditions depend on which solver you're using. But when you go and apply it, the real work is in static analysis and in having students chase all the optimizations. Right now we're working on LLVM. I'm sure Javier can have his own experience of where the work is, but we're not really fully verifying it. So was it a good for? I mean, this is like university tools that become obsolete because whenever, like, we started with the Open Research Compiler and the closed it, we went through many compilers since then. And I'm not sure that there's anything that is really running right now as we speak. But there was actually a use for it. And that goes way back. And I was spending some summers in Intel consulting in the formal verification group, and Moshe Vardi was actually in a different group, that is equivalent checking group. And they had this problem that Intel develops chips, and there's Pentium 4 and 5 and whatever, but in between each two major progress, like two Pentiums, there are mini micro changes. They add a cache line, for example. So each of those small changes is accompanied by software that utilizes this little enhancement. And it's impossible for them to keep software for each of those successive changes and to deliver the right software updates to each of to wherever those chips are. So rather what they do is that when they improve the software, when they use the new functionality, they say, hey, but for the old software, just don't use it. And then comes the issue of backward compatibility. They want to make sure that the new software working on the new CPU will work on the old CPU the way the old software did. And this is their backward compatibility. And they hired me to create translation validation for that. this is not exactly the framework that we're working on. Those microprograms are very low-level, machine-oriented, sequential control flow. Sometimes they're executed out of order. Each of them implements a single macro instructions and registers, and they do it by means of micro instructions, which are called UOPs. And abnormal termination is something that is very common. It needs to be dealt with very explicitly. So those UOPs are 3 address operations. They interact with the hardware. They have jumps like gotos, which can be either internal, external, or indirect. That is computed only at runtime. The target address is only computed at runtime. So we model it with its own intermediate representation language. I'm sure it had a name, where, of course, the first class citizens are bits and bits vectors because our working registers. There are conditional assignments and gotos and all that. Each UOP is implemented by a template, and I'll soon give you an example that has a signature and a body. But what's new that there is a very explicit treatment of side effects. And each of those successive improvements in the microarchitecture, each has its own template file. So here is an example. It's not perfectly typeset. Here is a flow. So let's say that the register 1 gets the content of register of the address at register 2 with the offset at register 3. And in register 4, you add register 1 and register 5. It's just an example. So we need to expand. What does it mean to do the memory read? And that's in purple. And what does it mean to do the addition? And that's in blue. And you can read all this, but let me just point you to the interesting thing. In line 3, after you add the register to figure out the address, you need to exit with address overflow. So that's a special exit with an overflow. And you need to send something, some values to this exit. Also in line 5, this is something that they do in microcode that is whenever a register it gets 0, some 0 flag, some system flag is raised. And you can see that this is in the add. And if you notice that I didn't include the integer overflow in the add, that's because I wanted it all to fit into one slide. So assume we don't have that. So this is a way you can expand. You can have those templates for each of those UOPs, and you can expand them. How do you create them? Well, you need the microcoders to create them because it's very difficult to tell. It's two things here, of course. This is microcode, so they'll never share it with us. In spite of all the DNAs, they will not share the microcode with anyone. And it's really good because then the burden on actually expanding the macrocode to templates is on them and not on us. But there are other little things that came in the way of the modeling. Microcode is an open system. We're used to closed systems. We always try to model things in closed system. And here we have a lot of environment interaction. Then there are out of order execution, but restricted out of order, but there still are. As I said, there's not a single exit. You can exit a program in different ways, which we call doors. And in each of those doors, you need to assign, there are different set of interesting things for that door. Also, the notion of equivalence to say that this is run exactly like it ran on the old machine needs some massaging. This is not the same. The environment is not the same. It's not even clear what to say that it runs the same way, because the same is not the same. And of course, once we created symbolic paths and ran them to SMT solvers, but there are often too many symbolic paths. Just think about it. If you have a program that just does if then else, if then else, if then else, you got exponentially many paths. So that would choke the validation process. So we needed to do some optimizations. I don't know, well, we don't have time. My favorite one is something called pruning, but we'll forget. And the thing, it worked. What I mean it worked, they found bugs. And they found bugs, and the microcoders loved it, and they kept on using it. And it was a great success. So I'll switch to a story, which at least at that point doesn't have much success. And this is internet protocols. Internet protocols are written in RFCs that are written in English, and it could have been any other natural language. Okay, Shankar would correct me. Maybe Sanskrit would have been really good for this. And their guidance for implementers, their guidance, they're not even very exact. They're ambiguous, they're contradictory, they're a mess. And what happens then? Independent implementers implement them, and then they go and test them for interoperability. Of course, those interoperability, which are called interop, and it's less of a mouthful, they don't, even if those things interoperate, they don't represent the full behavior that is allowed in the specification in those documents. Of course, they do any compliance check. You can't guarantee that it will interoperate with future implementations. This thing led to security bugs and some other problems. But what I found is the scariest, that eventually those implementations become the de facto standard. If you want to implement a new protocol, you need to go and make sure that it interoperates with the old ones. So this is work with Ken Macmillan. We thought about the network-centric compositional testing, which is called NCT for this purpose, which is again a teaspoon of formal methods. It's just really not a lot. And the idea is that we will manually, blood, sweat, and tears, it's really hard, create formal specification of on-the-wire behavior. What I mean on the wire is as an observer would see the traffic, which is not what's really in the RFCs. You need to extract it. Then using randomized constraint solving and SMT solver, we'll get randomized automated tests for implementation. So this acted really good because this the randomization acted as an adversary. And of course, we found mistakes in our specification and we had to refine the specification, but we also found lots of ambiguities in the RFCs, and both implementations and the RFC were corrected accordingly. And this test allowed actually to check implementations for compliance. So what's compositional about it? So we make the assumption of input of one processor treated as guarantees to the output of the other, the usual way. Here, usually processes are client and server, but I'm just saying usually because we have some flexibility to define our processes. So here is the traditional composition rule that assume P, M1 guarantees Q, and assuming Q, M2 guarantees R. So the parallel composition of M1 and M2 will guarantee R, assuming P. The point is that this parallel composition establishes an implicit channel between M1 and M2. And Q is a fact about something that is happening in the channel. But the role of Internet Protocol is to create this channel. Those channels are not given. We can't assume anything about those channels. There is no one-to-one correspondence between processes and addresses. The protocols are specified in terms of transmissions, not in terms of processes. So we can't apply the rule, and we have to come with a compositional rule that will fit the circumstances. How am I doing with time?
Well, you have maybe 4 or 5 minutes to finish, and then we'll switch to questions. Thank you.
Okay, thanks. I just wanted to know. So we came with a rule that depends on backward assumptions and some global specification. The gist of the rule was that each process guarantees the specification, assuming the others did not violate it. And that really means that the earliest violation cannot be the process's fault, and therefore there is no earlier violation. So this is the proof rule. And I'm just skipping that there was another issue of the packets being too long and taking too long time to generate them for Z3. So we did something that we call dependent field extraction, realizing later that it's used for a totally different thing in a totally different computer science area. But the idea is to try to separate the constraint, to try to solve as much as possible locally, and then combine the stuff, and that created great things. And I'm skipping it. And then we applied it to Quick, which is a new protocol. It's been for 5 years, 4 years now, going under RFC revisions. Of course, they want to do everything better, reduce latency, do better congestion control, do everything better. And it's a lot of the internet is now running on Quick. But the standardization, when we started working, was in version 7. I think that we got our results, what about version 12? Now it's version 34, draft 34, that is also been renamed RFC 9000. And the draft specification is very problematic. So we wrote specs in IBM only for a partial set of Quick because we didn't need to do everything. But for some things, we didn't do the specification. We rather restricted and did real implementations. For example, TLS 1.3. Nobody has the specifications. And it will be it's a project harder than specifying Quick to go to TLS 1.3. So we just took an implementation, of course, by virtue of that restricting the behavior we got. And we applied it, and we found bugs, and most of them were new at the time, and some exposed security vulnerability, which was sweet. So there was an issue of client migration, and the client kept migrating from one address to another, and the server could not keep up where the client is. Then what really, the reason we found it is because we only allowed 2 addresses for the client. So the randomized testing kept flipping between those 2 addresses when we tried to check the migration. But what it actually exposed is a DOS vulnerability. And indeed, when I looked recently on the document, they do have what I think is an explicit treatment of that, to say the server stop sending too many things, because that will expose you. Actually, the group at ITF were very responsive to the things we sent them. They're very excited, and they wanted us to do more and more and more of it. Several of them even seemed interested in doing it themselves, but I'm not sure that anybody did, because I haven't heard about it. There is a group in Galwad that is interested. But I think that the message you're trying to convey is, hey, those documents that you write only are providing guidance for implementation, but you're totally ignoring what does it take for implementation to be correct. We want the on-the-wire behavior to be given by the ITF, not by us. It's not a job for academics to do. And okay, so the takeaway. We don't need a lot of formal methods to make difference, to get really better results in different areas. We do have a major hurdle, and this is language. So whether it's microcode that we're not allowed to see and cannot understand, or whether it's RFC documentation that it's kind of a natural language, and I say kind of because it doesn't have even have the usual semantics. There are musts and should and all that. It's not like the way we're used to. But I found that the impact is direct proportions to how much the audience has an express need for the work. So if I go back to this science of using science, which is mainly about medical experimentations and psychological and medical experimentation, they ask, do the research results scale to larger markets and settings? And I think for us, it's again the scalability in the application domains. So which application domains can benefit from our methods? Then they ask, when we scale to broader and larger, again, what I commented out are medical specific, should we expect the same level of efficacy? And I'm going back to what Amir asked in this very first meeting about usable verification. Tucker, you may remember that somewhere in the South, Charlottesville or something. And there he said, it's okay to do small, like little v verification if we can make it more usable and more, and that more people could actually use it, giving up precision, that's okay. And the third question to ask, and I have no answer to, is what are the important threats to scalability? And I have no answer to that. So I think that's my last slide. So thank you, and I hope I made it in time. Yes, it is.
Thanks a lot, Lenore. That was a nice conclusion slide. Do we have questions? Well, I'm not seeing any raised hands or anything in the chat, but I hope, yeah, I'm using the web client. Oh, yeah. So Supratik, please ask your question.
Yeah, hi, thanks, Lenore. Great talk. I had a couple of questions. So the first is, you mentioned about randomized constraint solving for generating the tests. So I was wondering what tools are used for that purpose, because most state-of-the-art constraint solvers, they zoom down into some corners of the solution space. So I guess they will not give you random.
What of the space? I missed words.
I mean, the efficiency of most modern SMT solvers, for example, is because they can zoom down into some parts of the solution space and prune out large parts of the solution space. So their solutions are not going to be random. They're going to be biased in some sense, right?
Yeah, okay, so the random is not random. The random is not, we don't know the distribution. It's kind of used Monte Carlo, but actually to pin down the distribution is a lot of work, and it's not clear it's worth it.
Yeah, I mean, that's the hard problem too. I mean, we've done a little bit of work on that, but generating solutions which are uniformly randomly distributed or almost uniformly randomly distributed, it's a much harder problem than just generating a solution.
Yes, and it wasn't worth it. You see, we got the bugs and we got the experiment working without worrying too much about the distribution. Okay. So yeah, we're fully aware we don't know it's a mystery random distribution.
Yeah. Okay. The second question I had was, when you talked about translation validation, it's beautiful work that you have. I mean, there are instances where the language standard keeps things undefined, right? It says that for some programs, the behavior is undefined. And I was wondering, how do you deal with that in your formulation of translation validation?
I personally don't, but I know people who do. And,
okay.
And so things like this, the microcode is pretty good example of, you can get into gory details. You choose the level of details. We always choose how far we go, right? So in most of the work about translation validation, we assumed, we ignored exceptions. We ignored, think about an optimization, for example, that you have a line that says X gets X over 0, and then X is never used. So many static analyzers will take this assignment out because X is never used, so we don't need the assignment, right? This definition is not used. But in fact, you just take the semantics of the program, you change it from an exceptional exit on 0 divide to 1 without. So it's always how far do you go? And in microcode, you really go to the gory details. And in most of the work I've been involved with, you ignore the gory details and choose your poison. And it's also how far do you want to go?
Yeah. I guess it depends on, how much of, as you said, how much of precision you want to keep, and perhaps, being too precise is not necessarily what we want in a practical application. We just want to.
It depends also, Ms. These turtles all the way down.
Thanks.
If I can add something, and actually Sanjiva Prasad is commenting in the chat similarly. Yeah, it's actually better sometimes to underspecify and leaves yeah, completely non-deterministically open and to do things like translation validation. Do we have other questions? You can just speak. I'm not seeing any hands raised. But yeah, please speak.
I had a question, and I was wondering whether anybody has some suggestion for answer. What are the threats we're facing to scalability?
Well, I'm afraid we would need like a couple of hours to really discuss that. So, so maybe Benjamin can start to set up. I would. My own answer is that it depends a lot on your techniques. I think deductive verification, for instance, lets you build from, compositionally. Your verifications can be very compositional, and if you do whole program analysis or model checking on big systems, then you often get state explosions and things like this. So I'm not sure this is the kind of answer you were expecting.
There is a hand raised.
Oh, okay. Sorry, I just lost the participant list. Martin, you wanted to add something?
I was just going to try and make a stab at answering Lenore's question. I think one of the threats to scalability is the economics of tool development. So about half the talks so far in this workshop, we've talked about using an SMT solver, right? Having been someone who works on SMT solvers, it's so hard to just get even the most basic support. Like if everyone who gave a talk committed benchmarks, we can make solvers so much better. But this is one small tip of the iceberg of the economics, is that it's great to have all these things to build on, but someone's got to keep them working. Someone's got to like do the development. A lot of SMT solvers are just like one or two people. Often it's not even their main job. We need to work out a way of funding the infrastructure for people to build on. And at the moment, like a lot of open source infrastructure, the economics are kind of based on goodwill and hope. And that really is a threat to scalability. I don't know if it's the kind of thing you meant, but we should try and answer.
Okay, well, I suggest we continue this discussion maybe at the break. There will be some separate rooms where we can talk further and discuss further between us. And so I suggest we move to the next talk, which is by Benjamin Pierce. So I'm not sure he needs much of an introduction. Where he's famous for his early work on tight systems. He literally wrote the book on tight systems, two of them actually, which are still great references as of today. And well, he's done lots of other things on data synchronization, lenses, differential privacy, etc. But I think one of his other major achievements was the Software Foundations series of electronic books, which really introduced and popularized the use of proof of systems for teaching and researching programming languages. But today he's going to talk about, something somewhat different and involving, I guess, random property checking and web servers. So Benjamin, thank you.
Thank you, Xavier. Yes, so I would like to talk today about something not entirely completely different from verification tools, namely specification-based testing. And this is, of course, quite connected to some of the things that we were just hearing about. So, so the title promises that this has something to do with the DeepWeb project. I think probably many people here know about the DeepSpec project. DeepWeb is the web server that was the main demo project for DeepSpec. And let me say just a little bit about DeepSpec for background for those of you that that hadn't heard about this project. So this is it's a project that's been going on for the last 5.5 years, funded by the National Science Foundation, and is just coming to a close. So it's the sunset days for this project, but of course not for the work that was begun and continued in this project. So here were the principal investigators, and here were the people that did most of the work. And the whole point of the DeepSpec project was the grand vision was to move or help move the field of formal verification and specification from point success stories, of which there have been many over the past couple of decades, to a more sustainable engineering practice at scale that is industrially interesting. And of course, the reasons for doing it now, or at least 5 years ago, no need to elaborate on most of these in this audience, but indeed, progress on enabling technologies was one of the big ones. And then one interesting thing about the Deep Specifications project was simply the word deep, which we coined early on to describe a particular style of specification that we felt was particularly useful and productive in this context. So for us, deep specifications are specifications that are formal, of course, that are rich. So they're not just type systems, they're full-bodied functional specifications. They are, here comes the critical part, two more critical things. First, they're live, that is, they're not specifications of models, they're specifications of real actual running code. And there's some kind of automatic check, whether it's machine verification of a proof, or whether it's property-based testing, or some other automatic check of correspondence between the actual code that we care about and the specification that we wrote. And then finally, we were interested, and again, going back to questions at the end, we were interested in scale. We were interested in whole system specification and implementation. And therefore, so of course, whole systems are built in stacks. And therefore, the specifications of each layer in these stacks are mostly, except for the very top and very bottom, the specifications are two-sided. That is, they're exercised both by the implementer of that layer and by the users of that layer above. And writing specifications that are usefully two-sided turns out to be quite a bit harder than specifications that just talk about an artifact from above or from below. Okay, so we were interested in specifications, in understanding the specifications, the engineering of such specifications, and their use in really building and validating system software. So there were many parts to this project at 3 different institutions, now 4 different institutions, but we felt it was very important that there be a single unified demo or unified case study that most people in the project were contributing to. And that was the DeepWeb server. So here was the structure of it. It's a very standard structure. The yellow bits are specs, the blue bits are code. The code of the web server, well, in fact, the 2 top boxes are C. The code in the bottom is BlueSpec or some other hardware verification language. The top level spec talks about what you see of a web server across the network. And the bottom level talks about transistors. And then in the middle, there are some intermediate specs, in fact, more than this, that talk about important layers. And it was really, we did a lot in this project. It was big, but the main focus was on understanding how to engineer these specs, the yellow bits. The goal at the beginning was one QED that would say this whole stack of C code implements the top level spec of HTTP and some application running over HTTP, assuming transistors behave like such and such. Okay, so so much for DeepSpec itself and DeepWeb. Now, what about testing? So testing comes into the picture for two reasons. One is that verification is hard and costly. Therefore, we want to spend our time as much as possible verifying things that are true. And a cheap way to find out whether the thing that you're about to verify is true is to test it first. So testing is important for the economics of the situation, to streamline the design loop and to make sure that we're, at least most of the time, trying to verify things that are true. And second, the top level spec for a system like this is itself a complex artifact. So a formal description of HTTP plus however some application is supposed to behave is not a simple thing. And it itself is going to need to be validated. How do we validate it? We validate it against ground truth, and ground truth in this case is stock web servers that are out there in the world being used by everybody, like Apache and Nginx. So we need a way of validating the spec against the ground truth. We're not going to do that by formal verification. We have to do it by testing. Okay, so testing, for many reasons, is a really interesting part of this picture, and it's what I want to talk about for the rest of today. So we want to add in testing. Let me close this bit by just talking for one more second about DeepSpec as a whole and the things that we learned and what we were able to achieve in terms of this layered web server. So we made a lot of progress. We built a fully verified web server. We wrote it in C, verified it using the Princeton BST toolkit. It is compiled using CompCert, of course, to RISC-V instructions, which can be run on a verified RISC-V processor. The high-level spec was indeed validated against Apache and Nginx. We found some bugs, of course, in Apache and Nginx. No surprise there. We managed to make, so one of the purposes of the project was to take separate efforts that had been underway and bind them together to get this one QED for the whole stack. So in particular, we succeeded in establishing a formal connection between a style of specification that the people at Princeton had developed and were used to, and that was embodied in VST, and a rather different style of specification. At Yale. They call it layer interfaces, and at Princeton they call it separation logic or concurrent separation logic. And we did manage to establish a formal connection there between the POSIX API in Princeton style and in Yale style. And then at the bottom, there was, at the beginning of the project, a pretty big gap between the way CompCert talks about a RISC-V and the way a RISC-V implementer would specify their top-level goal interface. So, and we closed that gap substantially by showing that by introducing a flat memory model for RISC-V in the CompCert toolchain. Okay, so this is what we achieved at a high level in terms of the web server. So you might be asking, okay, did you get to the one QED? Sadly, we did not get to the one QED. There are some bits missing. First, the TCP stack that the demo uses is itself not verified. The rest of the operating system is, but not the TCP part. Ultimately, one would want to just cut TCP out of the trusted computing base by running the whole thing over cryptography, but we haven't done that yet. Second, we in some situations, in some parts of the proof, we achieved morally a single QED without actually being able to check the whole thing together. And the reasons for that are twofold. One is remaining differences between the Yale style of specification and the MIT style. And then the other at the higher level is between, I'm sorry to say, the Koch versions assumed by the Princeton toolchain and the Yale toolchain. So so those gaps are reasonably small, but not yet completely closed. And then there's one more gap that's interesting to me for today, which is that we ended up needing to use specifications that were not literally identical for the verification part and for the testing part. They are very similar. They were written by the same people, so we have some confidence that they correspond, but they are not. They have no mechanical relation. So so this is disappointing, and it's something that we are continuing to work on hard, and it's what I want to tell you about for the rest of the talk. So so very quickly, I think everybody probably knows about this. So there are lots of varieties of testing based on specifications. There's enumerative varieties, random, concolic, et cetera, et cetera. The basic idea of all of them is the same. So you write down the specification in some mechanically checkable, automatically checkable form, like a Boolean function that you can just give it an input and it says, yes, that input is okay. You apply it, in the case of random testing, for example, you apply this function to many randomly generated inputs. And then if you find a bug, you minimize it and report it to the programmer. A canonical example of this in the random testing style is quick check. There are many variants of quick check, basically for every language you could think of course, including Koch. And this is the one that we use for our work. Not to make too heavy water of this, why is specification-based testing good? Because it's cheap, but it gives you a lot of bang for the buck. And it's nice for present purposes because the style of specifications is similar to the logical style that we want to use for verification. Okay, so what style of specification should we choose for this effort? Well, here we have a bit of a dilemma. And this dilemma is the reason why we actually at the moment have two different specifications that are not automatically related. One is that for purposes of verification, at least with tools like VST, a nice way to write down the server, a nice way to write down the specification is as a model implementation. So you give a reference implementation. Of course, it's non-deterministic because the specification is underspecified, and because the server can have internal state or make internal decisions that you don't see from the outside. So you have a non-deterministic reference implementation, and then you say that what we mean by correctness is the implementation needs to refine the specification. That's nice for verification. It's also nice because it's really easy to extract a reference executable implementation from the specification, and you can use that in all sorts of ways. But it's not so easy to test directly, because what you want for purposes of testing, you need to generate a client that's going to interact with the server and say yes or no. And therefore, we need to think about, if we're going to have a single thing, we need to think about how do we extract sort of both the server style, server view style reference implementation and the testing harness from a single thing. Okay, so the challenges, just to summarize, are how do we extract this test harness from the reference implementation, or extract both of them from a common thing? And then we're going to need, in particular, what is this test harness? It is an input generator. And here we get into all the problems with how do you tune the distribution and so on, plus a validator for test outputs. And then the second major set of questions is, how do we deal with the non-determinism arising from the server's own non-determinism and from the fact that we're testing across a network? Okay, so since time is short, I'm going to concentrate on just two of these, the validator and the non-determinism of the server. And since we're all friends here, I want to show you a little bit of work in progress. This is really up to the minute. The student and I were working on it late last night. And try to give you a super simple model of this situation, just concentrating on validation and dealing with non-determinism. So I'm simplifying away. I'm not dealing with the network or the operating system. I'm not dealing with the fact that web servers communicate over many channels. I'm going to assume there's just a single request response protocol. The queries and the responses to them are just going to be bits instead of anything more structured. And I'm going to assume that all the non-determinism comes from inside the server. So the picture of the world is, we have one specification. It has two alternate semantics, one that gives you a server and one that gives you a validator for runs of the server. Now, over here, we have a test generator. For right now, I'm not saying where that comes from. It just generates lots of tests. Each of those tests is a sequence of queries, which are sent to the server together with, and it's convenient just technically, for the non-determinism of the server to be controlled externally by an oracle. So what the server gets is a sequence of queries together with a sequence of, you can think of them as coin flips or choices that are determined externally by some oracle. The server then is a deterministic function from those two things to a sequence of answers. And then the job of the validator is to say, okay, given that sequence of queries and corresponding sequence of answers, is that a good, does that run of the server satisfy the spec? Okay, so a little bit of technicalities. So let's say that the queries, the answers, and the choices are each just bits. So they're drawn from a set with two elements, each one of them. Now, what's a server? A server is a thing that you give it a query and one bit of non-determinism, and it gives you back an answer and a new server that you can use for asking further queries. And of course, this obviously generalizes to presenting the server with a sequence of queries and a sequence of non-deterministic choices, and you get back a sequence of answers. For instance, so here is the world's simplest programming language for specifying servers. The language has two instructions. One is called flip and the other is called compare. And a program, or you can think of it as a specification of a server, is just a list of those instructions. The specification itself, the specification says how must a correct server behave, or how may a correct server behave, since we're refining, since correct implementations can refine, how may a correct server behave? And here it is. If the program runs out, then the server should just send back A1, which is the true bit of answers. If the program begins with flip, it should also just send back A1. It always sends back A1 when it's executing a flip instruction, but it remembers the current choice, C. And then if the instruction is compare, it compares the query that it's given with the internally stored choice. If they are the same, that is, if the query is true and the internal choice is true, or the query is false and the internal choice is false, then it sends back yes, A1. Otherwise, it sends back A2, no, and then it goes on. Okay, so that is the world's simplest specification of a server, parameterized on a particular, so this is a class of servers parameterized on a particular program that the server is executing. Now, what about validators? So a validator takes a query and an answer. So it takes the first step of the list of queries, the first answer that came back from the server, and it says, it doesn't say yes or no. It gives you a list of further validators. If that list is empty, what that means is no. That means there are no runs there's no way of continuing that run that's valid. That was a bad query and answer. Or there might be multiple validators going on from this, each one of them embodying a different assumption about the hidden choice that was made on the server. Okay. Now, we can write down a validator semantics of the same specifications. And so what I'm doing here is, I apologize for many details quickly, but I hope you're getting at least the big picture. What we're doing here is for each program, we're extracting a server. So the function I gave a couple of slides ago is the server semantics of programs. Server semantics of, I'm calling them programs, but you can think of them as specifications also. Here I'm giving the validator semantics. The validator needs to, on a compare, it needs to notice what the server is doing and say, oh, that means that if the server is saying yes to this query, that means that the server must have originally made such and such choice internally. And whereas on the flip, it has to guess. So that's why there are two elements of the list here. The validator has to split and say, well, the server might have chosen true or it might have chosen false at this point. Okay, one last bit of technicality, which is the main theorem, and we've actually proved this theorem late last night, which is we can say that a validator accepts a list of queries and a list of answers if either they're both empty or if some validator if the validator returns a list of further validators and some element of that list accepts the rest of the queries and answers. And now the main theorem is that the server extracted from a program and the validator extracted from the same program exactly characterize each other. That is, the set of runs generated that can be generated from the server is exactly the set of runs that will be accepted by the validator. Okay, so coming back up and getting to the end. So there are lots of questions. My first question is this whole setup a known thing? Does everybody know this? Not everybody knows it because we didn't know it, but perhaps lots of other people know it. If so, I would love it if somebody told me what its name is. And then the next part is, how do you extend it? So the language of specifications of servers that I wrote down is obviously very impoverished. How do you extend it to a full-blown specification language? And can you still play the same trick of giving the server semantics and the validator semantics? And then finally, what about the test input generator? And in particular, this is another side project that I'm happy to talk to people about. But one of my students is thinking about how we can use machine learning to tune the parameters of the distributions that come from generators. Okay, that is enough from me, and I would love to hear your questions.
Okay, thanks a lot, Benjamin. Do we have questions? And just speak or raise your hand if you want. Oh, Peter. Yeah, go ahead, Peter.
Hi, Benjamin.
Hi, Peter.
So, hey, I'm very happy to see that DeepSpec has managed to glue some things together, even with some gaps. B, on this, so is this setup known? I'm not sure if it's exactly known, but if you're not aware of the work that some people here did on NQSB, you might want to look at it.
NQSB.
So this was David Kalaper-Mershiniak and Hannes Mernart and some other people, slightly me, but really them, who set up something not in a proof resistant, but just in pure OCaml code to produce a specification of TLS 1.3 that they could both execute as a server and use as a test oracle. So it's the same kind of structure.
Good, thank you. I knew I would get at least one back from this group.
So Benjamin, just to add to what Peter said, first of all, I think the deep spec results are, bloody marvelous. I think this is quite an amazing accomplishment. Modular, the gaps, which I think are inevitable. I think in a project of this scale. Would it be fair to say that the setup you have is that from the spec you create three components. One is a driver, one is a generator of behaviors, and another is an acceptor of behaviors.
Yeah. Yes.
Yeah. And another piece of work that I might reference is there's a project in France a few decades ago called TGV, which was kind of a reactive testing framework.
TGV like the train?
Like the train, yeah.
Okay. Thank you.
All right, more questions or more answers to Benjamin's questions?
Please feel free to send answers later. Thanks, everybody.
Peter Mueller has a question.
Yeah, thank you. So maybe another. May I?
Sure, go ahead.
So maybe another pointer to related work. So as far as I know, Google uses implementations in domain-specific languages as formal models of like more optimized implementations. And then they run techniques like concolic testing over those models to generate the test cases that they run then also on the optimized implementation, then they compare results. So I think that is at least somewhat related to your approach.
Yeah, that sounds very related. Do you have a Googleable tag for that?
I'll get back to you in the chat or something.
Thank you.
Okay.
All right, Xavier, we should go on.
Thank you. No, that's fine. Well, maybe the next speaker, Ranjit, can set up and start sharing his screen. Not sure there's any questions left. Anyone wants to add something? All right, so let's move on to the third talk then. So it's given by Ranjit Jhala, who is at the University of California in San Diego. And well, again, he doesn't need much of an introduction. He became famous quite early with his work on software model checking and the BLAST tool in particular. But he's also with the inventor of liquid types, which was one of the first attempts to combine deductive verification with functional programming languages. So two things that are extremely dear to my heart. And so his work with liquid types has been pioneering. And well, he's going to talk about something, I guess, involving both verification and some amount of programming. So thank you, Ranjit.
Thank you very much, Xavier, and thank you, Shankar, and everyone for inviting me. I told Shankar yesterday I was very worried about Zoom fatigue, but the talks have been most invigorating. So thank you. So I guess someone has to bring down the average. So here we go. Okay, so I'm going to tell you about this line of work. It's about types, deductive verification, etc., and functional programming. Xavier, not to worry. It is kind of about a tool and experiment, but we'll get to that point. We'll see how far we go. Okay, so this work is about, it's sort of motivated in the context of this liquid types and liquid Haskell verifier. There is a tool. I just wanted to make sure that a tool exists. I'm not actually going to talk about liquid Haskell for the majority of this talk. It's this kind of Daphne style, what Ruston likes to call an auto-active verifier, right? So there's going to be lots of code that I actually want you to understand. So kind of lean in and let's look at some examples. So here's the kind of really kind of simple example of the kind of thing you might want to do with Floyd-Hoare logic, which is a very kind of intimidating thing to say when Tony is in the audience. So imagine I have this little snippet of code. I have a max function. It takes two arguments, 10 and 20. And then I store the result in P. So var P is max 10, 20. And then I want to assert that P is greater than 0. Okay. And then again, I have this max function. Max just computes the maximum of two numbers. There's no magic there. Minus 10, minus 20. And now I want to assert that the result n is less than 0. So now the question is, how do we sort of verify these assertions? And I'm going to give you a kind of 30-second tutorial on Floyd-Hoare logic, right? So if this was my max function, then what you might do, this is just checking, is x greater than y, return x else y. What you would do in a kind of deductive verification style is you would specify a kind of contract for max, and then you would use it to verify the clients, right? So in this case, the contract, if you wish, looks something like this. It says, oh, you can call max with any inputs. So this is requires true is the kind of syntax many of us are familiar with. And then you would say that it returns a value r that is, say, either of x or y. I mean, you could be more precise. You could somehow say it's the larger of x or y, but for our purposes, it'll suffice just to say the result is either x or y, right? Great. So in my world, I'm going to sort of switch that around, and instead of writing requires and ensures, I'm going to write it like a type. So read this as it's a function type. It takes two inputs, x and y, both are integers, and it returns a result r, which is also an integer, such that r is equal to x or y. Okay, great. So far, so good. Now let's go and look at how we might verify the client. So if I say P is equal to max 10 or 20, this is just classic Floyd-Hoare, right? What we're going to do is we're going to plug in the post condition at this call site. And so I'll say, oh, I know that P is equal to 10 or P is equal to 20, because that's what my contract for max said. And now I want to prove this goal that P is greater than 0. And so I get this, verification condition. So I get this formula in blue, P equals 10 or P equals 20. Does that imply P is greater than 0? And of course, an SMT solver will say yes. And we can be happy. The program is verified, right? So we love SMT solvers. We don't pay for them, as Martin has perhaps quite accurately said. I've sort of worked them in various guises and software model checkers and these kind of autoactive verifiers. We saw this wonderful talk on symbolic execution yesterday. But you knew there was a but coming. I have a big problem with them, okay? And the problem is that once you start thinking of writing more interesting kinds of specifications, you can't do that in a way that preserves SMT decidability. So let me give you some examples. So I'm going to show you a bunch of examples where you can either have decidable sort of verification conditions, or you can have modular specifications, but not both. Okay, so here's the first exhibit. Minor tweak of the max example, I now take as input a list or an array or whatever, a collection of numbers. And now I have this maximum function, which is just like max, except it works for a collection. Again, I want to prove the same thing. If I call maximum with this list of numbers 10 and 20, that the result P is greater than 0. But if I call it with negative 10 and negative 20, the result is less than 0. Okay. Now, here's my implementation for maximum. You can imagine how this is done. There's some collection, you loop over the collection, you increment your max and so on. It's not super important. You sort of call max one by one, and then you return the result R. But what's the specification that I might write that's going to let me prove my two clients? That is, at one call site, the result is positive, at the other one, it's negative. The most obvious one you might go for is something like this, that max returns some result R that is greater than X for all X in X's. If you think about it, that's kind of true. I mean, there's two reasons why I don't like it. First of all, if you think about it, it's not strong enough to prove my negative, the thing where I call maximum with negative numbers. The second thing I don't like about it is it has this pesky for all quantifier. Okay, so I'm going to sort of continue to rant about quantifiers in a moment. Another thing you might say is, well, there is some value inside this collection X's such that the result is equal to that value. Again, this also has a quantifier. And here is the kind of, I don't know if Cesare is still here, but the moment you mix SMT formulas and quantifiers, that is not a happy combination. That's just, we kind of steer clear of that, because many of the nice guarantees that we get from SMT solving, sort of fast decidable verification and so on, they just go out of the window because you get into this kind of quantifier instantiation, spiral, as it were. Okay, here's another example of where you really want to write some nice modular specification, but I don't know how to do that in a kind of classic logic without using quantifiers. Okay, so here's a function that takes, this is, I first used this function when I was programming OCaml. It's an init function. It creates an array of size 100, where what you do is you pass in the size, which is 100, and then you pass in an initializer. It says for each index I, fill in the value I plus 1, which is not very important. This is a lambda, right? This is JavaScript syntax for lambda. And now what I want to prove is the following assertion, is that if I take the array A, if I call this for each, it's a kind of, it's a combinator that iterates over all the elements of the array. If I take the value V of I, then that value V of I must be greater than I. So I want to assert this. And so now my question is, here's my init function, which, again, looks quite, standard. I create an empty array, I loop over it, and I fill up R of I with F of I, return R. What's a contract that I can write for this? Again, now we're getting into all kinds of trouble. We have, first of all, a universal quantifier for all I. And then I have this F, which is now somehow like a logical thing that's appeared in the contract. This is just, both of these are kind of toxic, a kryptonite for my verification conditions. I'll show you one more example of, a very canonical kind of function. It seems like a toy function, but it's of course a widely used function. It's just the sort of standard functional composition, the dot or circle operator, okay? So compose here is literally just function composition. And here what compose does is it takes two functions, A, this first one, so think of it as a lambda A goes to A plus 1, lambda B goes to B plus 1, B minus 1. And I just want to assert that F of 10 is equal to 10. Okay, so obviously this is true. But again, if I want to write a modular specification, here is my compose function. It takes F and G, and it returns a function that I'm just using this syntax to, as a kind of syntax of maximum familiarity for everyone. A new function that takes as input A, calls F of A, saves that in B, calls G of B, and returns that as C, right? Obviously, this is much simpler to write in the lambda calculus. I don't even know what a requires ensure clause for this would look like, let alone how you would put it, in a kind of nice Floyd-Horry style. Okay, so this is my problem. I love SMT solvers. They're really good for sort of nice first order contracts, but the moment you have higher order functions or you have nice quantification, sort of things go out of the window. And then it turns out is a really kind of limiting kind of thing, right? So the problem that we observed is that in the sort of setting where SMT solvers work very well, the property that you care about is hardwired into the contract. So what do I mean? Let's look at this. So you can say things like requires that some input X is greater than 0, or you can say things like it ensures that some result is greater than 0, right? These are nice quantifier-free formulas that the SMT solver can digest quite easily. But what I really want to do in all of those three examples that I showed you is to abstract over the specific properties, okay? So instead of hardwiring properties, these sort of first order predicates into the contract, I really want some notion of parametrization over properties, or you can think of it as a kind of higher order contract. Okay, so next, let's see how we can do that. Let's go back to our exhibit A, which was the maximum function. It took a collection X's, right? And then iterates over them. Here's what I'm going to do. What I want to do is to write a contract that looks like this. For all properties P, I require that if you give me a collection such that every X in X's satisfies P, I don't know what P is, but some property P, right? Then I can guarantee to you that the result satisfies P. Okay, so I want to be able to write this as my specification for maximum. Okay, so let's see how we can actually do that. While the goal of this work is going to be, how can I let you write specs like this while preserving all these nice properties of sort of SMT decidability? And then towards the end of the talk, if I have time, I will show you an example of how this lets you build some really cool tools. Okay, so here's a complicated bit, right? I want to first say things like every X in X satisfies P. And then I want to, just even describe what it means for something to satisfy P. Here's what I'm going to do. First of all, let's just look at, just like we're going to sort of borrow inspiration from plain old type systems here. Okay. So in a plain old type system, how do you specify this very simple contract, which is I require that every x in x's is an integer and the result is an integer. Very simple. It's just a totally standard kind of type. You would write something like this. X's is an array of integers and the result is a single integer. Okay, I hope everyone is following me so far, right? Now we have to somehow add that bit about the properties. So here's what I'm going to do. What a refinement type lets you do is it lets you say integer satisfying p, okay, as a predicate like so. Okay, so I write it as v is an integer such that p of v, where crucially think of this p as an uninterpreted sort of function symbol. Okay, so I'm going to sort of abbreviate that just for space as int in sort of array notation in brackets p. And so now I can go back and write my specification, the thing that I had up in English, as this kind of, this kind of polymorphic refinement type that says, if you give me an array of integers, each of which satisfy p, then I will promise to give you back an integer satisfying p. Okay. So let's see how we can now verify the library. So by which I mean the maximum function. So here's our maximum function. And remember, the whole problem was how do we sort of make sure verification is decidable? Here's what we're going to do. So my goal is, given this function, I want to verify this particular signature for all p. X is an array of int p. I must give you back an int p. Okay. So I get to assume, because x is an input, that x is an array of int p. Now, that's just from the input type, right? I want to prove the goal that the result r is an integer that satisfies p. Well, I'm just sort of going to borrow sort of inspiration from my type system over here, right? So if I know that r is x's of 0, then I know that x's of 0 is an int p, because remember, x's was an array of int p's, okay? Now, if I know that, this is one of the possible results, right? So r is equal to x's of 0. Remember that int p means int such that p of x is true. And so x such that int p really is the same thing in logic as saying p of x, right? And so popping that back into my, we're all familiar with this. And so popping that back into my, my sort of proof goal, what I get is something like this. If I know that p of x is of 0, and I know that r is equal to x is of 0, can you prove to me that p of r is valid? And as you can see, this proposition is valid, right? This VC is valid purely using decidable SMT reasoning, because here p is just an uninterpreted function. Okay, and the SMT solver is quite happy to check this for me. And you do the same thing, right? When you have the max, essentially the same thing happens. We use the same signature for max, which is the result is equal to either the old value, in this case r, or x's of I, which is the second parameter I'm passing in. X's of I is an int p. The old value of r is also an int p. This again gives you a nice decidable VC. P of x is I, p of r old, r is equal to the old value or equal to the new value. Can you prove that p of r? Once again, this is just completely decidable reasoning. We get to verify the particular maximum function. Okay, great. So it's quite easy to verify these kinds of higher order looking specifications if you just think of these p's as uninterpreted. Next, what we're going to do is let's go and see how I can check the client. Okay, what do I do about my maximum, where I call maximum with the positive and negative inputs, right? So here was my, I'm going to move the video out so I can see my own slides. So the problem is at the call site, I have this for all. And this is, again, it's kind of think of it like parametric polymorphism, but for refinements. I have this for all p. And what I want to figure out is, how can I instantiate the p at each of the individual call sites, right? What is the concrete property or invariant that I can instantiate the p with at the particular call site where I call with 10, 20, or -10 and -20? So here's what I'm going to do. Okay, so at each call site, what is the exact value of p? And the trick we're going to do is to essentially find a way to instantiate the p using horn clauses. So let me just illustrate with an example. At each client site, I'm going to pretend that each for all p gets instantiated with a horn variable. Okay, so if I have my contract, that's going to essentially give me a bunch of horn constraints. So let's look at a concrete example. This particular for all p, I'm going to make a new horn variable, let's just call it K1, okay, where K1 denotes an unknown, it's an unknown invariant. I'm going to solve for this invariant, okay? And so now at this particular call site where I call maximum with +10 and +20, maximum behaves like x's is an array of integers such that k1 of v holds for each of those integers. And you get back a result of integers v such that k1 of v holds. Great, okay? So now if that's how maximum behaves at each call site, let's see what happens with the specific constraints from the call. So if I call var x as maximum of 10 and 20, essentially what's going to happen is that 10 must be an integer such that k1. Okay, so 10 and 20 must be of the type array of values such that k1 of v holds, which once you use some subtyping, you essentially get that 10 must be in the set of values such that k1v, 20 is in the set such that k1v, which is to say k1 of 10 must be true and k1 of 20 must be true. Okay, so 10 and 20 must satisfy whatever this magic property is. Finally, at the return, I know that x is also in the set of values v such that k1 of v. And so what I know is that a k1 of x must imply that x is greater than 0. That was my goal in the assertion. Okay, and so now what I end up with is this nice system of horn constraints. K1 of 10, K1 of 20, K1 of x implies x greater than 0. And you will just have to take my word for it that there is a way that you can sort of solve this out, right? I do the same thing at the second call site. You can solve this out. You get a bunch of, you get a solution where K1 of V is V greater than 0 and K2 of V is V less than 0. Okay, so and this is essentially the same reasoning that we do in, I mean, for people familiar with these terms, the way you sort of solve these constraints is, there's various forms of abstract interpretation that you might use. I'm personally my personal favorite is something Shankar invented a long time ago called predicate abstraction. In particular, there's the kind of Flanagan and Rooston's Houdini algorithm for just finding the strongest solution over some set of ground predicates. I'm ignoring all questions till the end, by the way, because I have a lot of slides. Let me just make sure I know what the time is. How much time do I have, Xavier?
Let's see, I'm kind of losing track. About, I don't know, 5 minutes, 7 minutes? Is that?
Oh, good. Okay, so let me just, I'll skip this bit. Okay, so the important bit is in the libraries, we want to parameterize properties of a contract. In the library, the parameter is an uninterpreted function. And in the client, the parameter is a horn variable. I only have 5 minutes. That's a bit of a shame. Okay, let's see. Let me skip over this part. Oh, skip. I want to go here. Okay, great. Wait, I want to skip all this. Sorry, give me a moment. Here we go. Okay. So next, what I want to show you is a trick where, remember the compose function, where I wanted to not just have these kinds of abstract properties, this kind of parametric polymorphism, but to introduce a kind of bounded quantification, if you wish, which lets me relate these refinements. So let's look at this compose function, which was my exhibit C. What type can I give it so that it lets me sort of verify that if I compose two things, I get this kind of functional composition of the, of the two postconditions of f and g. So here's what we're going to do. Okay, so here's the plain old type for compose. It says you transform A to B's. That's what the f does. Second thing transforms B's to C's. And so the function composition transforms A's to C's. This doesn't tell me anything about properties. Okay, so in order to kind of talk about properties, what I'm going to say is for all properties P, Q, and R, if the first function produces a postcondition, a value B, that is related to its input by this proposition P of A, and the second function produces some result that is related to its input by the proposition Q of B, then the result must produce some value C that is related to A by some new property R of A. Okay. So now, if you try and verify the library, what's going to happen is that you won't be able to verify the library. Let me just, let me cut to the speed up a little bit and just show you what the constraints are. You end up with having to prove the following verification condition where P, Q, and R are uninterpreted propositions. And of course, this is not valid. Okay. So now the important trick is when the formula is not valid, what you can do is in order to make it valid is to put this as part of the type signature. Okay, so what I'm going to do is I'm going to add this as a kind of quantification constraint to the precondition. So I'm going to say chain P, Q, and R is P of AB and Q of BC is equal to R of AC. And the moment you do that, Now, of course, you can fix the specification, okay, and it all works out. The SMT reasoning all works out. It's all decidable, etc., etc. And you can verify the client. So when I have this compose, the same kind of horn clause machinery essentially works out just perfectly, except that you now get the extra horn constraint from that chain condition as well. Okay, let me now skip to the tools and experiments part. And show you some really nice things you can do with this. So we sort of found this out in a series of papers like, I don't know, 6-7 years ago. And then over the last couple of years, thanks largely to Nadia, who is the next speaker, we found some really nice applications. Okay, so here's the application. I will just describe the application and not how any of the technical details. So the goal here is you have a bunch of web applications. You will sort of write web applications like Hotcrap or EasyChair or what have you. Venmo, you're sending people money, and I don't want my mother to know what I've been spending money on Venmo. And there's all kinds of nasty ways you can sort of leak information in these web applications, largely because it's very hard to tell who you're sending data to and where data came from and so on. For example, here is Hotcrap. Here's some code from Hotcrap, which has a bunch of these kind of little security checks. Should we be sending data to this person? Is this person authorized, and so on? They're all kind of mixed into the business logic, okay? And so when your code, which is this black stuff, is sort of mixed in with the orange stuff, you can't really tell, does my code actually implement some high-level security policy or not, okay? And so what we did is we found this way, thanks to Nadia, where you can rip the policy out entirely from the business logic and just write it off on the side. It's just a very small document, which is like 1% of the code base, right? And then you can verify the application against that particular policy. Okay, the policy is way smaller, far easier to audit. And so the way all of this happens is we build a web framework, and the web framework has these components, right? You have the client, you have the web server where the computations is happening, and then you have the database, which is where all the sort of sensitive data is stored, which you associate with a policy. And essentially, you can implement a kind of full-blown information flow control system. That's what this particular Storm web framework does. That lets you kind of separate the policies from the business logic. And the way all of it works is essentially, it's just a library with one of these constrained refinement type APIs. So I cannot possibly explain how this works because it's not one, but two separate papers, one written by Nadia last year, who figured out how to use these constraint types essentially to do information flow control. And then this new paper that we have that's going to come out in a couple of weeks, where we show how to do sort of SQL queries, right? And I'm not going to try and explain this. The important bit is that you can essentially use these constraint, these kind of refinement parameters to precisely track the semantics of SQL queries and track information flow in a way that then lets you verify these web apps with very, very little programmer overhead. So that's it. I'm going to stop now. I hope I didn't go too much over. I will say all of this there is a tool. It's on GitHub. You can check it out. There's lots of people who use it. We get more user requests, bug reports that I know what to do with, as Martin was complaining. The really nice thing is it's all implemented as a compiler plugin. And so, for example, with these web apps, you're just building the web apps. And essentially, the security policies just get checked every time you try and compile the code. And if you want to learn more, then here's a sequence of 4 papers that I will refer you to. So let me stop here and look at some of the many questions that have piled on in the chat. Thank you.
Well, thank you very much, Ranjit, for a nice talk, and you are perfectly on time. Congratulations. All right, so do we have questions? Yeah, I see in the chat there are some discussions ongoing, and that you can also raise your hands. So Peter, would you like to, you raised your hand, would you like to start?
Yeah, sure. So Ranjit, thank you very much. This is really great work. Let me nevertheless express that I disagree with your motivation, right? I mean, there are lots and lots of examples that building SMT-based verifiers that use quantifiers all over the place is not so hard, right? Everything based on Boogie, Viper, Daphne, Corel, which is used in Microsoft heavily. It has been used in really large projects like Ironclad, Iron Fleet, Armada. I mean, there are lots and lots of examples where people put this kind of technology to work very successfully. So nevertheless, I mean, you have something great, a great achievement there, but I think your starting point is not accurate in that sense.
You know, Peter, the quote, just because something can be done doesn't mean it should be done. I'm being facetious, of course. No, of course you're right. Lots of amazing things have been done. I don't deny that at all. I just think that the fact that they rely on this heuristic is unfortunate. And I would like to see how far you can go without having to rely on quantifier instantiation. That's the way I think about it. I really want to, the necessity is the mother of invention type of thing, right? I really want to tie my hands behind my back to see, what you can do without quantifiers. Because I think, there's this, I gave a talk recently. Anyway, I don't want to get into this rat hole. I agree with you, except that I disagree with you. Let me just.
Fair enough. Thank you.
Okay, Matthias, would you like to ask a question?
Yeah, thanks for your talk. I would like to ask, what tool do you use for solving the horn clause constraints, and what is the bottleneck in practice? Is it the horn clause solver?
What is the bottleneck in practice? Yes, I mean, the bulk of the time is spent inside the horn clause solving, that's for sure, if that's what you mean. In the entire verification endeavor, yes, the vast majority of the time is spent inside the horn clause solving.
Yeah, okay, thanks. And then I would like to encourage you to submit some benchmarks to this horn clause competition.
Yes, I will, I promise. I've been promising Nikolai that for a very long time. Actually, I gave him a bunch a long time ago, but I will give him a fresh bunch more recently. Yeah.
Thanks.
I think Victor has a question, but I don't know if Nadia has answered.
Discussion in the chat involving Victor in particular, but I don't know if he wants to ask a question live.
I just want to make noise in the chat, actually.
You're doing a great job, but you can also ask a question.
Thanks, Ranjit. Of course, this is a great and very influential line of work, and it's great to see also these recent contributions. So, yeah, my question, I guess, was more like, what do you think makes horn clause solving better than quantifier instantiation? Well, sorry if I'm bringing this back to rat hole, but
I think
it sounds like you say this is not heuristic, right? But of course, there are various systematic approaches to quantifier instantiation as well.
Correct. So, in fact, where I in fact agree with you perhaps and Peter is I am giving you my own quantifier instantiation heuristic. But
yeah, that's a very good point.
What I'm doing, right? It's entirely my own quantifier instantiation heuristic, but the heuristic is entirely syntax directed, which I think is a nice place to live. So it's really not fair to say. I mean, obviously there's quantifiers somewhere, but essentially what I'm trying to do is push all the quantifier instantiation heuristics to be entirely kind of syntax directed, which I find to be it's really a kind of user interface kind of thing because they are syntax directed, by which I mean they all live at the type signature level, right? And where I sort of call functions or do pattern matching and so on. It turns out to be a much more convenient way for the programmer to kind of think about how to do the quantifier instantiation and even think about how the spec should be written.
But then another question is, I guess some people go even further in taking away the functionality of SMT solvers and saying disjunctions are also problematic. And in fact, we have had this experience recently, a bit surprisingly, in combination of bit vectors with uninterpreted functions in Z3, which is apparently being addressed in the new engine. But for example, I think work of Emina, right? I think in general symbolic execution, right, it tries to take charge of disjunctions. And I'm wondering if maybe disjunctions do not play so much of a role in liquid types because unlike this, as Shankar was pointed out, right, they extended the predicate conjunctive combination of predicates into disjunctive, right? And that's what was used in BLAST and so on, right? Am I right that now in liquid Haskell, you went sort of back to conjunctions, right?
Correct. So we also, I mean, you can have disjunctions if you put them in yourself.
Right,
Like
but then they're sort of black box, right? I mean, they appear.
You don't make up new disjunctions, exactly.
Yeah.
Because that, I mean, going back to Matthias's question, that could, you don't want the SMT solver to be doing case splits if you can help it.
Mhm. And my other question is that you do like this separation between specification and type. Sorry, the implementation, Haskell, and then the types. And of course, this is this is a common thing to do in type systems. And but at the same time, right, it's quite similar, right? You have some properties. You have Boolean expressions in language and so on. And so, you know, if I just pasted some gist here for the compose function, right? I mean, in system like Stainless, we just unfold things, right? And you could say unfolding of functions, just a rather trivial thing, is also syntax-driven approach. And so certain things, yeah, it's not modular, maybe, right? But then you don't have this problem, or is it a assumed guarantee? Do you have to repeat the specification? Because to me, there's no simpler specification of compose than compose itself. I mean, you can have a theorem about compose that is more complicated than compose, but.
Right. So Victor, I picked compose.
Before you respond, Ranjit, before you respond, can I interrupt for a second? And since this is the last day, and Gemma and Paul will be leaving soon.
Sorry, I went overboard.
No, that's okay.
I need to catch up with
thank them. Yeah, I just want to thank them so that you know they know that their work is appreciated by all of us. Thanks, Gemma. Thanks, Paul. And also, I'd like to thank the various organizers in the Newton Institute who've helped with this, starting with David Abrahams, the director, Christy Mark, the assistant director and the deputy director, and Samantha Shekel and Megan Snow. So I just wanted to thank all of them. Okay. Go back to Ranjit.
Yeah, thanks very much. Gemma has been especially kind with me, I have to say. I am very grateful. So Victor, you are absolutely right. With compose is slightly misleading. I picked it just because it's the smallest example that has an interesting kind of horn constraint in the signature. You could totally inline compose. But once you have larger things where, for example, like filter or any of these things I sort of flashed by for the information flow stuff, right? Where you're doing SQL queries that return collections of records, you can't unfold there because the objects are all unbounded. So don't be kind of misled by that. You're absolutely right. With things like compose, you could just inline it. But in general, you don't want to do that once you have larger, for the usual kind of modularity reasons.
Thanks.
Okay, well, maybe we can take one last question and then we will stop for the break. Martin, you raised your hand?
Yeah, I mean, I think Cesare had his hand up first, but I don't know if he wants to.
Well, he seems to have disappeared from my screen, so so go ahead.
So if I understand correctly, you said, well, this is sort of a syntax guided quantifier instantiation heuristic. Could I just implement something like this in an SMT solver? If I was picking up the same patterns you were using, could I just use the same tag, but just implement it sort of the other side of the boundary, as it were?
So when I say syntax directed, I mean syntax directed in the way that, say, Benjamin might refer to it, which is to say, guided by the structure of the program syntax. And so, I mean, if you look at just the if you look at ultimately what goes into the VC, I guess it's like, where you're drawing the line. So much of the quote unquote, the syntax that I'm referring to does not anymore live once I'm in just the verification condition, right? I just think of the verification condition as a kind of an amorphous blob where much of the program syntax has been stripped away. So I think the answer to your question, Martin, is probably yes, you can, as long as you were able to somehow carefully preserve enough of the high level, the surface syntax or whatever of the program itself, to kind of recover it in the SMT formula, if that makes sense.
That's a great answer. Thank you.
Can I add a quick comment to this?
Yes, please, go ahead.
So I actually, I'm in a position of having to agree with Ranjit on a lot of things he said. the fact that sometimes the original application knows better. So the question, I think it goes back again to trying to find a sweet spot. And that's why, once more, we should probably, the two communities, well, we're in the same community, but, people focusing more on SMT on the developer side and people focusing more on SMT on the user side should talk more about this, because I think we all need to find that sweet spot and figure out how far. First, it's not clear to me how far you can push what you're doing right now. So, talking more would be definitely a way to address it. So maybe we should have a workshop or something like that.
Okay, well, thank you for your comments. And so I suggest we stop here and take a break. So nominally, we start again in 15 minutes, but maybe Shankar will give us a little bit more time. And so thanks again to the three speakers and everyone who participated. Oh yeah, and there are breakout rooms if you want to, or actually I can create breakout rooms. No, I can't. Yeah, I can.
So let me pause the recording.
So here is where program synthesis comes to the rescue, right? The idea in program synthesis is that how about we only require the developer to write the specification, and then we automatically generate both the code and the proof for that specification. And, that sounds great that, sign me up, of course. Maybe it's a little bit idealistic, of course, to think that it will work for, to automatically generate all of the code that we need for those verified systems out there, right? But at least we can hope that maybe some parts of these systems, we can make it easier to write using this technique. And of course, the great thing is now, the specs are hopefully easier to write than at least to write both the specs, the code and the proof, right? And that we get this verified code in the end. But unfortunately, the hard part is, of course, it's a very, very challenging task, right? And so even for the easiest of domains, program synthesis is hard. But especially for this domain, it's even harder because this low-level code is verbose, it's unstructured, and it has all these pointers and aliasing that are hard to reason about formally, right? Okay, so how do we even begin to tackle this problem? So in this talk, I will present SUSLIC, which roughly stands for synthesis using separation logic. And the SUSLIC approach to this problem is basically how do we solve these challenges of reasoning about pointers and the code being unstructured and messy. Well, we have our solution sort of has two main components, right? We use separation logic to write our specs and reason about the synthesized code, right? And so you have heard about separation logic earlier this week, for example, in Peter Miller's talk, right? And so if you know anything about separation logic, you know that it's specifically made for reasoning about pointers and aliasing, and it makes this kind of reasoning easier, right? And then how do we address the problem that, well, we have this vast search space for code, right? Because the programs are so unstructured. Well, we, instead of searching in the space of programs, as most synthesizers do, we use deductive synthesis, which means that we search in the space of program proofs, right? With the hope that those proofs are much more structured and the space is smaller because we are basically only searching in the space of correct programs, right? And we can use specifications to guide synthesis. All right, so in this talk, I will introduce SUSLIC to you first by just showing you a really hello world example, right? So this will be an example of a swap function. And these kind of basics of SUSLIC were published in our POPL 19 paper, if you want to see more details. And then the main part of the talk will be about the cool new way we have of handling recursive functions using something we call cyclic program synthesis. This is fresh off the press, will appear at PLDI 21. All right, so let's start with our hello world example. So let's say we want to synthesize this function that swaps values of two distinct pointers. So something with a signature like what you see on the screen. So by the way, Suslik uses as its target language like a very simplified sort of featherweight version of C, which I will just illustrate throughout the talk. Right, so how do we explain to the synthesizer what do we want this procedure to do? Well, we want to say that before we start executing it, so in the start state, we have these two distinct pointers, X and Y, that store some values. Let's call them A and B. And in the end state, we want those pointers to still be there, but the values to be swapped. So we can write that in separation logic by writing a pre and a post condition in separation logic, right? So so in the pre-state, we can write the following precondition. This precondition consists of, and we can write this post-condition. The preconditions consist of two so-called points to assertion. So in particular, this points to assertion says that, so points to assertion describes a heap with a single memory cell whose address is X and the value stored in it is A. And then these two points to assertions are joined by the secret sauce of separation logic, what's called the separating conjunction, right? And the separating conjunction means that those two assertions hold of disjoint parts of the heap, right? So that's how we say that these two memory locations are disjoint, right? And we use ghost variables here. I will use capital letters for ghost variables in this talk, to talk about the values that these locations store. Okay, so we can give this specification to Suslik, and let me show you what happens if you do that. Where did my Suslik go? Oh no. Wait. Oh, sorry. Just a second. Here it is. Okay, so this is the web interface to Suslik, right? So you can give it the specification, which is exactly what I showed you in the slide, and you can run it. Sorry, that takes some time to start the JVM, but in a couple of seconds, it will give you this program back, which basically what it does is it first reads from both of those pointers into fresh variables, and then it assigns the variables into those pointers in the swapped order, right? Okay, so let me just quickly go through how Suslik achieves that, right? So to give you a sense of what this deductive search is, deductive synthesis is. So deductive synthesis is a synthesis as proof search. So what are these proofs, right, that we're searching? So these are proofs in a special program logic that we designed that is called synthetic separation logic. And that's basically a version of separation logic that is tailored for synthesis, right? It's more restrictive in some sense, so that we can get better guidance from our specs, right? So it's a proof system for a judgment that we call transforming entailment. And transforming entailment looks like this. So the meaning of this judgment is a state that satisfies P can be transformed into a state that satisfies Q using a program C. I mean, I'm omitting some details, but so this is the intuitive meaning of this judgment. So if, of course, all of you are familiar with Hoare triples, and you can ask, what's the difference between these and the Hoare triple PCQ? Well, there is no difference. We basically just rewrote it in this way so that it's more intuitively clear that what we are doing is we are producing a program given a P and a Q, right? But programs, like the soundness guarantee of this judgment is that the program that we produce will satisfy the Hoare triple PCQ. All right, and so of course the program logic is defined using some inference rules for these judgments, right? And so we have some, I can show you some simple rules just as a sample of what they look like. So for example, if we know that the precondition and postcondition are both just the empty heap, then we know that we don't need to do anything, right? So then we generate skip, right? So this is our axiom. It's called the EMP rule, right? So the idea is that the synthesizer will transform the initial goal and simplify it gradually until it reaches this state in which it has just EMP and EMP in the pre and the post condition. And now we can close the derivation with this rule. Another rule that we have says that, well, if the precondition and the postcondition both share some part of the heap that is the same, right? Then we can simplify our goal and simply generate a program that goes from P to Q, and then the same program would work for this more complex goal, and this is called the frame rule, right? So it's true in separation logic because C cannot touch the part of the heap that is described by R. And I'm showing you slightly simplified versions of these rules, but that's the gist. Another rule that we have says that if in the post condition, we have a points to assertion where X points to some program level expression that contains no ghost variables, then we can simply write E, that expression, into X, right? And we will end up with matching points to assertions in the pre and the post, and this can be then solved by the frame rule. So this is called the write rule. And then symmetrically, our read rule says that if you see in the precondition that you have a variable pointing to, you have anything pointing to a ghost variable, then you should read this ghost variable out, right? Because then you can do something with the variable in your program, right? So this let statement would read from the address X, right? And then this is called, and we will replace all occurrences of A with this new fresh program variable Y in the specification. And that's our read rule. So these are very, very simple basic rules of syntactic separation logic. But even just using these 4 basic rules, we can solve our swap problem, right? So we start with this transforming entailment that has our initial pre and post condition. Right, so at this point, the only rule that applies really is the read rule, because we have in the precondition something pointing to a ghost. So we will read it out into a program variable A1 and replace A with A1 everywhere. Similarly, for Y points to B, we can apply the read rule. Now we see that in the post condition, we have some variables that are pointing to non-ghost expressions. So we can apply the write rule, right, to write B1 into X, for example. So this is what we do. And now we have matching points to assertions in both pre and post, so we can frame them out using the frame rule. And then similarly here, we again apply write and we apply frame. So we end up with the goal emp to emp. So we can apply our emp axiom and generate skip, and then collect all these statements that we emitted, and voila, this is how we generated the swap program. All right, done with the first part. So this was, of course, a very simple example, right? This is not particularly interesting. Let's see how we can generate some more interesting programs, in particular recursive programs, right? Using this new technique that we call cyclic program synthesis. So this part will have 3 subparts in it. I will start by telling you how we can describe more interesting data structures in Suslik using inductive predicates, and then I'll tell you about generating programs that manipulate those interesting data structures. All right. So far I only showed you programs that manipulate, static data structures like individual heap locations, but how do we describe dynamically created unbounded data structures? Well, in separation logic already has a very nice tool for it. It's called inductive predicates, right? So if you want to describe something like a linked list, which is what is depicted on this picture, right, we can introduce a predicate called list that takes as input the head location of the list. And this predicate will have multiple cases. So the first case will say, and those in Suslik in particular, the syntax of predicates is such that the different cases are guarded. So here it says that if X is null, then the heap is empty, right? So this corresponds to the empty list case. And then if X is, the start pointer is not null, then this heap contains a dynamically allocated block of size 2. And then in this block, the first location stores some value, and the second location stores some other value, which is the next pointer, Y. And then at that next pointer, we have another list, right? So this is the recursive case of our predicate. In here, the one slightly non-standard thing, if you know separation logic, is this what I call the block assertion. So you can think of it as the permission to deallocate this block. So this basically is just used to keep track of dynamically, like malloc allocated memory, as opposed to just memory that's there and we cannot free it. But it's not very important. That's just how we write things in Suslik. All right, so now that we have this way of describing linked lists, right? So maybe we can generate something a bit more interesting, a bit more interesting program. So for example, a very simple program we can generate is a program that deallocates the linked list, right? So let's see, that's our second example. So here, that's our spec. As the spec says that in the precondition, we had a list at location X, and in the postcondition, we don't have it anymore, right? Which means that we need to get rid of it. And let's see what Zuck says to that. So of course, it generates a recursive function that says that if the head is null, which means the list is already empty, there's nothing to do. Otherwise, we will read the next pointer, we will make a recursive call on that next pointer, and then finally we free the head. All right, so how would Zuck generate this code? Well, of course, we can't just use it with the rules that I already showed you. We need some special rules. We have extra rules for handling these inductive predicates. So the very first rule that we'll apply here is called the open rule. Open rule just unfolds the definition of the predicate in the precondition, and it will unfold this definition according to, because the definition had two cases. Open will generate a conditional with two branches, and then we'll have a sub goal per branch. So the first sub goal just corresponds to the empty list case, which is trivial. We just close it with emp. And the other branch corresponds to the non-empty list case. And then in this case, one thing we can do is we can free this this head, because we have a memory, a block assertion, and all these points to assertions. So, but after we're done freeing it, right, what we are left with is this specification, right? So we have the tail list, and it needs to go to emp, right? So at this point, what should we do? I mean, we could open that list again and then repeat this whole song and dance again, but this wouldn't save us because we will end up with the same goal again and again, right? So because this data structure is unbounded, so we need some way to generate a recursive call actually from this goal, right? So, and how do we do this in Zuck? So this is exactly where the cyclic synthesis idea comes in, right? So to generate recursive calls, we use this idea of cyclic proofs that has been actually used in separation logic before in those papers that you can see on the slide. And so what are the cyclic proofs? They are proofs that are not exactly trees, they are graphs. They have backlinks, right, to some other goals. So you can close a goal by backlinking it to an identical goal elsewhere in the tree. And so how it would work here is, well, we basically notice that this goal looks just like our root goal, right? And so because of that, I mean, up to alpha in naming, and because of that, we can close this goal simply by linking it back, right? And so what this backlink does in terms of program synthesis is it generates a recursive call, right? So that's kind of the semantics of those backlinks. And of course, it's not always sound to form those backlinks. Whenever you form a backlink, you have some soundness condition to prove that something basically strictly decreases every time you go along the circle. But there is a super nice and elegant automata-based soundness condition in cyclic proofs that they have developed that is actually very, very powerful and allows you to encode a lot of different termination metrics. And so we use an existing tool called Cyclist to check the soundness of those loops for us. And you can see more details in the paper. All right, and now finally, the most exciting part of this talk is that what we realized is that cyclic proofs allow us not only to just enable cool non-trivial termination metrics and have this very elegant way of handling recursion, it also allowed us to solve sort of a long-standing challenge in program synthesis of recursive functions, which is automatically discovering recursive auxiliary functions. So let me show you a third example where I can illustrate this. Okay, let's say our task is to flatten a binary tree into a doubly linked list at this point, right? So I also noticed that, well, let's say in my implementation, because the nodes of the tree and the nodes of the list actually have the same structure, right? They all records with 3 fields. I can do this transformation in place, right? So I can just traverse the tree and switch some pointers around, and without allocating any new memory, I can convert a tree into a double linked list. All right, so how would I do that in Suslik? Well, in Suslik, I can define these predicates for tree and for double linked list. So here, what I haven't showed you before is that our separation logic assertions can also have what's called the pure part, which just talks about it has like a pure first order formula attached to it, which talks about the content, let's say, of the data structure, right? And those predicates can be parameterized. In this particular case, they're parameterized by the set of elements of the tree and set of elements of the list, right? So we're basically saying that we want the double linked list to have the same set of elements as the tree used to have. And so the second parameter in the double linked list is the back pointer, which here I use an existential variable for this, which is irrelevant. If you want to know why this is happening and why this is not null pointer, you can ask me after the talk. So not so important, but another thing that is important is that I want the tree and the list to start at the same head pointer, right? This is how I'm expressing that this should be in place, even though this doesn't guarantee that this is in place. But if we really want to guarantee it, we can also take away the ability of Suslik to allocate memory, so that's also fine. The main point here is that this problem would actually stump existing recursive program synthesizers, right? And this is because they are unable to discover recursive auxiliaries, and this program actually requires a recursive auxiliary. It cannot be solved just using self-recursion with this spec. Okay, and so let's see what's going on here. So I'm not going to show you formulas anymore. I just switched the pictures because I'm sure you're tired by this time in the talk. So here I'm sort of drawing my synthesis goal as pictures. So I have this tree in the precondition, and I want this list in the postcondition, right? So again, we will open the tree, and the empty tree case is not interesting. So we'll look at the non-empty tree case. So here we have the left and the right subtree, and then our node, root node. So here we can easily make recursive calls on the left subtree, on the right subtree, but at this point we end up with 2 lists in the precondition and 1 list in the postcondition, right? So we need to somehow append those lists together, and appending lists is a recursive function itself, right? So that's why a tool that can only make self-recursive calls cannot actually solve this problem. However, Suslik can solve this problem, right? So what I would do next is, well, just like, so let's go back to this goal that we just now said is kind of problematic for other tools to solve, where we have 2 lists in the precondition, 1 list in the postcondition. Well, Suslik would just, is undeterred. So of course, the one thing that it can, by the way, let's call this goal G. We will reference it later. So one thing that Suslik can do is, again, open one of those lists, right? And pattern match on it. So if that list L was empty, then we don't have a problem. That is a simple problem because we have 1 list in the pre and 1 list in the post. So that's fine. But if this list is non-empty, right, then we have this situation here where we have the head of the list at L and the tail of the list at some new pointer N, right? So at this point, Suslik notices that this goal looks familiar, right? In particular, if you remember the goal G that we had before the last conditional, right? It also had 2 input lists and 1 output list, right? And it had some extra node that we also have here. So at this point, Suslik can, so except that, one of the lists is now smaller, right? So we used to have this list L, and now we have this smaller list N. So at this point, Suslik can cycle back to the goal G, form a backlink to the goal G, which will in terms of synthesis, correspond to a call to, but this time not a top level recursive call, but a call to an auxiliary function, right? That we will call helper. And the spec of that helper function is the GoG, to which we are linking back, right? And of course, what this helper function does, according to its spec is, well, it appends those lists L and R and X all together, right? So we are now replacing this
Nadia?
with... Mm-hmm.
Nadia, you have about a minute.
Okay, that's fine. I'm almost done. So we're replacing this backlink with a call to helper. Then, of course, the code after helper is very easy to generate because we only have one list left. And then once we've done this, because we have linked back to G, we will extract the code that is generated from G into a separate helper function. And then replace, in the original code, just really replace this whole part of the proof with a call to helper, and we're done, right? So we have generated flatten that uses a recursive auxiliary helper. And if I had more time, I would show you the demo, how Zuck actually does it, but you'll have to just believe me, or you can go online and try it yourself. All right. And so what else can this technology do? Well, we can generate nested traversals such as list sorting, deduplication without any extra hints from the user. We can handle non-trivial termination metrics like sorted lists, like merging sorted lists, and we can even do mutual recursion, right? With this cyclic synthesis. So for example, we can do operations on a rows tree, which is a tree that arbitrary arity tree that stores its children in a linked list. And so we also have an invited paper coming out at CAV 21, where we sort of collected all this stuff all together, and we have some cool benchmarks there that you can look at. But basically, we synthesize programs over all of these non-trivial data structures with up to 32 statements for programs like binary search tree translation to sorted lists, and with up to 12x ratio between code and specs. So the specs are usually much more concise than the code that comes out. And all of this is synthesized in some reasonable times, like within 2 minutes. And, we have a bunch of future work too. So for example, we would like to handle more classes of auxiliaries. We would like to be able to provide some guarantees about the programs that we generate, such that these programs are efficient and readable. And of course, the search is always a bottleneck, and we would like to be able to have less brittle heuristics, for example, via machine learning. So that's all that I wanted to talk about today. Happy to take questions.
Okay, questions? So I think we already have a hand raised. Sanjeeva?
Hi, thanks. Nadia, that was a very interesting talk. And, it sort of took me back many years when I used to see proofs and programs written in concert. But this one is actually synthesizing. The question I had is the kind of program that you synthesize assumes a particular machine on which it's going to run, an idealized machine. But in practice, it's probably going to be a finer machine with relaxed memory models, many cores, probably sharing a cache, an L2 cache or something. And what if the property that you're worried about is a security property? I'm thinking about Roderick's talk the other day, that could you have things go wrong because of race conditions, and could you have things go leak information? So that was one question. And the other question is about the flatten program. I was wondering if a generalized zipper on trees might give you a different way of looking at how to synthesize programs. Thanks.
Thanks. Yeah, very good question. So as for the first question, yeah, absolutely. You're absolutely right that there are a lot of assumptions that we're making about, so we are only reasoning about sequential programs, right? So we are not currently reasoning about security properties at all, right? So one direction in which we definitely would be interested in expanding this is handling more classes of programs, for example, concurrent programs, right? That would be very interesting because there are a lot of advances in concurrent separation logics, right? So it should be possible to just take whatever advances there are in separation logic and just use them here for synthesis. We are not doing this at the moment, right? So, and being able to address also more interesting classes of properties like security also would be very cool. So I have some experience kind of adding information flow properties and security properties to refinement types, which is what Ranjit just mentioned earlier in his talk. So perhaps it's possible to add this kind of properties to these kinds of specs as well. And the second question was about, zippers, right? So indeed, they're probably, so that's actually a really interesting question. One thing that, so we were really very excited when we discovered this, cyclic proofs trick. At this time, I have to admit that we don't really have a good notion of what is the class of programs that it can actually handle, right? And you might be right that like, this is the same class of programs as those zippers can handle. I'm not sure, right? So this is definitely future work. And if anyone here has ideas for how to actually figure that out, I would be very, very happy to hear your ideas and to collaborate.
So the thing that Sanjeeva mentioned, Reynolds gave a beautiful talk at ESTT 2010 on what's called proof outline logic. And if you look up, I think there are other separation logic papers where he talks about proof outlines as well. But,
proof outlines?
Proof outline logic. So the idea is that the structure of the proof matches the structure of the program.
Well, right. So here it's basically always like that, right? So we cannot even possibly generate anything where the structure of the program does not match the structure of the proof. I guess here.
Shankar, I actually was thinking back to the first day when Tony was talking about quicksort plus X plus Y, where the Y was the machine on which you're going to run it, and you don't know what kind of adversarial environment that machine actually presents to the program. So while your program might be a sequential program, you want to run it in isolation. You don't want information of this program to sort of leak to other parts, even though it's a sequential, simple program like Swarm. But maybe you don't know what adversarial environment it's running on. I think we just need to maybe look at that idea a bit more.
Sure, yeah. Those could be additional constraints on the synthesis.
Right. I mean, this is certainly true, but I think this is kind of orthogonal to synthesis in some sense, right? So the good thing about this approach is that whatever advances people develop in separation logic, right, we can bring them in and just factor them into the proof.
So Nadia, I started the recording late. So would you do me one favor and just display a title slide?
Sure. Oops. Oh, God. I have...
And if there are other questions in the meantime, please feel free to pose them. Okay. So yeah. I just want to make sure that we've introduced the speaker as Nadia Polikarpova from UC San Diego, speaking on the synthesis of safe pointer manipulating programs.
I see Supratik has a
question.
Yeah. So this is really fascinating work, Nadia. So my question is that the same precondition to postcondition transformation could be done perhaps by a nested loop written in not so smart way or a non-nested loop written in a smart way. So are there any guarantees that you can provide? And I'm just wondering, what are the kind of what's the price that we pay for
yeah, this is an excellent question. And we have, so right now, the answer is right now, we're not giving any guarantees about the efficiency of these programs, right? And in fact, as soon as we enable these recursive auxiliary abduction, right, we see it immediately that we're getting inefficient programs, right? It didn't used to be such a problem in synthesis because the search space was smaller, right? And then all the programs it generated were linear. But now it loves generating quadratic programs where it can generate linear programs, for example, right? Like in this tree flattening example, right? Because there's a better way to do it. There's a linear way to do it, and it's not doing it in this way. So what our plan is for that, however, I think there's actually a good a way forward here. So because we have experience in resource guided synthesis, we'll call it, in the functional programming domain, right? So with the refinement types, we found a way to integrate the resource analysis into the synthesizer so that you can give a bound. For example, you can say that I want a linear program, and then the synthesizer does this reasoning about resources while it's searching, right? And it's actually pruning out those inefficient programs early, right? So, and we think that something like that can be very easily also added to SOSLIC because you know, separation logic is very conducive to adding this kind of resource information to it as well. And there is work on separation logic with time credits, for example.
Okay, thanks, Nadia. You know, that was great. Enjoyed that a lot, and thank you for that. Thank you. So let's move to the next speaker. So Armando Solalazama is our next speaker. Go ahead and share your screen, Armando. So he is at the MIT, and he graduated from UC Berkeley, I think around 2008 or 9. You know, he's the inventor of CGIS and many other technologies, Sketch as well, you know, that have led to just a whole body of work on synthesis across many, many different domains. So today we'll be talking about the creation and evolution of the Sketch synthesis system. Armando.
Thank you. Thanks for the introduction. So, given the topic of the workshop, I decided this would be a good opportunity to talk about some of the aspects of creating a tool that you know, sometimes don't end up showing up in the paper. And so we have this Sketch synthesis infrastructure that we have been really building incrementally for, at this point, in the past 15 years or so. It's been a pretty long running project. And so I wanted to talk a little bit about the infrastructure aspects of this and some of how you know, we've gone about developing this system, right? So at a very high level, if you look at this as just a piece of software, it's about 531 Java source files and over 100,000 lines of Java code. And then on top of that, we have about 200 C++ source files, close to 70,000 lines of C++ code. So by this point, it's actually a pretty substantial piece of software, piece of infrastructure. And by now, there's been about 13 graduate students between Berkeley and MIT who have, and actually even some at Tufts at this point, who have actually invested effort working with this code base, not just using it as a black box, but actually working on the source code and having their contributions incorporated into the code. So as you might imagine, and I know pretty much everybody here has built software you know, tools before, it you know, it takes a while for a project to build up to this kind of scale. Now, the project, as it started, it you know, this code base was never intended to be of either this size or this scale. It you know, it was really meant to be just an experiment to prove the point that you could actually leverage SAT solvers to help you find tricky pieces of code. And so it turns out that actually the origins of this code base go back to an even previous project, which is called StreamBit. And the basic idea of this project, this was actually my very first research paper, as a graduate student at Berkeley. And the idea was that we wanted to help people write very low-level bit twiddling type of manipulations. And we cared in particular about these programs that manipulate streams of data, but treating them as a stream of bits, looking at them one bit at a time, and doing things like permutations, dropping bits, or doing Boolean operations on the bits. Turns out you see some of these things in things like ciphers or error correction codes. So this was actually the example that we used basically in every single talk of the paper, where imagine you have a stream of bits and you want to drop every third bit in this stream, right? And it turns out there's ways to do this that are very efficient if you take advantage of all the world level parallelism that you have available. What's I think significant here is that the actual infrastructure that we built in order to do this basically required you to take in these programs written in a high-level language, translate them into data structures representing these bit-level manipulations, doing some Boolean reasoning over them, except at this point, I did not know that SAT solvers were actually a thing. So this was basically leveraging a fairly ad hoc solver that I had written in C++. And then in order to actually write these programs and make them look nice, I realized that the source code for the original Streamit project at MIT was just sitting there in the Streamit website, and it was open source. So I was able to just take that code, it was all written in Java, and basically turn this compiler that was designed to do manipulation of streams of data and make it spit out some temporary file that we could actually then process in this in the solver and generate some code for you. Now, it turns out as a tool, this project was a complete dead end. The scope where this particular of problems that this tool could actually solve was extremely minimal and very, very restrictive. But it turns out that after working on this for a bit and realizing that this was not going to go too far, Sanjit had just started as a faculty member. Sanjit Sashia had just started as a faculty member at Berkeley. And we had this idea of what if we use a solver instead, a SAT solver to actually try and solve these synthesis problems and do something that would be a little bit more general. And so this is how Sketch came about. And it turned out that we wanted to get something up and running for the deadline. And I already had all these C++ code that had all these data structures to represent Boolean formulas and to manipulate them. And I also already had this front end that was written by somebody else, but could handle if statements and while loops and for loops and assignments and arithmetic and things like that. And so it became very easy to just use this to build up from this existing kind of dead-end project. And if any of you have ever looked at the Sketch code base, you can see that there's still some vestiges of this very old code and this very old project that really had nothing to do with synthesis. And it sort of gives you an idea of how some of these major projects can sometimes come about. Now, the Sketch language itself turns out to be actually a pretty powerful thing. So the basic idea, the basic philosophy behind the language was that we would just take a simple imperative language and extend it with one simple construct, just the ability to have an unknown that could be solved for a scalar, some kind of either Boolean or integer constant. And the idea is that you could then find a value that would make, for this unknown, that would make this program work. so that all the assertions are satisfied for all the values of the inputs. And when you view it like this, it sounds a little bit lame, because at the end of the day, most of the time, it's not just one little constant that you're trying to figure out. You'd actually like something that helps you come up with more meaty details of an algorithm. But it turns out that just leveraging that simple feature together with some very aggressive partial evaluation and just very traditional language constructs, the ability to have high order functions, the ability to have the ability to do recursion, can actually allow you to do some pretty powerful things. For example, this has been kind of a canonical example for Sketch for a while. The idea is, imagine you have some kind of an array and you try to divide it, partition it over P processors. So you're trying to come up with a beginning and end for each of these processors. Well, it turns out that if you just do N over P, what ends up happening is that the last one gets stuck with all the leftovers, and you end up with something that is imbalanced. And so turns out there's a better trick. So we can actually, in Sketch, write a partition function where we tell it, this is my processor ID, this capital P is the total number of processors, N is the length of the array, and I want to get as output the beginning and end of the range. So these are just going to be passed by reference, and they're going to be update inside. And so since we can see here that for this problem, doing N over P is not going to work, and N over P plus 1 is also not going to work, it seems reasonable that we might actually need a branch in this code. And so we can write a sketch where we say, well, we know there's going to be a branch, and we're going to check for something. And in both sides of this branch, we're going to be checking for the beginning and the end. And we also know that there are some things that we're probably going to need to use, like all the variables that we have available, maybe also N over P or N mod P. And so, but the thing that is very powerful is that we can actually build these libraries of generators. So for example, we have a library function called expression, where we can give it a list of terms that it can use for that expression. So it can be lowercase p, capital P, N over P, and mod P. And we also tell it that it can also use plus and times. And then separately, we can give it a test harness that says, I want all the assertions in this test harness to be satisfied, right? And so for any lowercase p and N and capital P, I want to make sure, for example, that if I partition then begin and end, I want to make sure that the difference between begin and end is not too much bigger than N over P, right? It's okay to be a little bit bigger, but not too much bigger. And I also want to make sure that if I'm not the last partition, then the next partition should start where the current partition ends. And I also want to make sure that the first partition starts at 0, the last partition ends at N, right? And with this, the system can actually search in about 5 seconds over an enormous space of possibilities, including constants, including many different arithmetic structures. This number is a little bit inflated because it accounts for the total number of unknowns that the SAT solver is searching for, but many of those unknowns actually code to just different forms of the exact same program. But nevertheless, you can see that it can very efficiently generate some potentially fairly non-trivial expressions. And all the scaffolding that went into actually writing those generators, those EXPR generators, all of those are written in the language, and all of that scaffolding is gone just to give you some pretty straightforward, clean expressions, right? So it's actually a fairly powerful tool. It turns out, actually, it's not as powerful as a programming aid, which is what we originally envisioned these to be. It turns out writing those generators, it's actually quite hard. And even if you can reuse them, often you find that you have to use actually somewhat different versions depending on the exact problem that you're trying to solve, just to make sure that you balance how big the search space is going to be versus how efficient it you can search. But it turns out we've actually been able to leverage it for lots of other application domains. For example, one application that we've been really excited about is reasoning about solid models in computer-aided design, and actually being able to take a 3D shape, just a solid 3D shape, and take a point cloud around this 3D shape and generate a CAD program that tells you how to construct that 3D shape through a series of geometric operations. But we've actually done applications ranging from linguistics to automated tutoring to program optimization. It's actually pretty surprising what you can do once you have the ability to discover arbitrary but small pieces of code. But going back to the point of how this actually came about. Sorry?
So yeah, you have about another 5 minutes or so.
Perfect. Yeah, so going back to the point of how this tool came about. So as I said in the beginning, the original hypothesis behind this project was we can leverage SAT to do these things. And one of the things we found very quickly is that's great for Boolean decisions, but even the simplest sketches require integers. Now, somebody with a little bit more vision than what I had at that point as a young graduate student I would have just used an SMT solver, except that seemed like a bit of a hard thing to do. And at the same time, just going and writing my own thing to BitBlast also seemed like a hard thing to do. And so instead, we decided to go for the simplest possible thing that we could do, which was just a one-hot encoding. Essentially, for every integer, just have a list of all the values that the integer can take, and a bit that says, is it that integer or this other integer? All of a sudden, it became super easy to encode all sorts of arithmetic operations. And it turned out that for the most part, a lot of the integer reasoning that we had to do involved things like this, where there's some Boolean decision, and some variable is going to have one value depending on, or a different value, depending on that decision. And it could actually be encoded really, really efficiently based on that. Several years later, we actually tried to just throw away the solver and replace it with a proper SMT solver. And it turned out that for the particular problems that we were solving, problems that actually looked like this, it still turned out that this encoding was actually much better. Now, I just tell this story to point to the fact that, you know, when you're building this kind of infrastructure, sometimes a lot of design decisions turn out to be just accidental of the thing that you're trying to do to get to the deadline as quickly as possible. But it is actually pretty important to then go back to those decisions and actually try to figure out, was that the right decision, and what is the right way of writing this? Now, one of the things that has been a challenge over the years is actually maintaining the infrastructure. As I said in the beginning, we did not expect this tool to last beyond the first paper. And you can tell if you've looked at the source code that it could probably be a lot better. But there were actually a few things that really go a long way towards a tool that is usable many years down the line and maintainable. One is to actually take the time to make it easy to compile and run on different machines. This is actually really, really useful when you're trying to get students to implement things in the infrastructure. Keeping track of sort of release versions and keeping separate the release versions from the experimental branches, so that you can actually go back to the implementation that was used for a particular paper. And finally, lots and lots of tests. Now, I think this is probably a good place to stop. I think I am actually out of time at this point, but I'm happy to answer any questions.
So thanks, Amanda. This actually brings up a lot of discussion points. Actually, right at the very beginning of your talk, Victor already had a question, so I'll let him ask it. Victor.
Oh, thanks. So this is a really very interesting story to see what's sort of behind this. And I wasn't actually aware that you maintained the tool for so long. So were you tempted ever to restart and say, because of what you said, well, code is maybe not so well written. Maybe if I made different design decisions, this would justify like restarting the project, or maybe a PhD student wanted to do that.
So one of the things that I have tried very hard is to make sure that the projects drive the infrastructure and not the other way around. And so in particular, when I'm brainstorming with a student or when we're trying to figure out, how to approach a particular problem, it should never be, oh, well, you have to use Sketch, right? Because that's our in-house thing. And sometimes we decide that, yeah, this is actually the right tool for the job, and we go and jump with it, And sometimes we decide that no, actually, it really makes a lot more sense to build something specific for that project. And that sometimes becomes infrastructure that now the student goes and maintains and now owns. And there's certainly many other projects that have started in my group that have nothing to do with the Sketch infrastructure. Just because it just didn't make sense as to use it for that. But usually some of the lessons that went into this can end up as part of those projects. For example, a lot of the neural guided synthesis work that we have done most recently relies on more custom infrastructure, but it takes some of the lessons of things that we have learned from these infrastructure.
And I guess it's really yourself and your involvement in the tool that provides part of this continuity.
Yes, that's right.
Student matters to get.
And I think that's a really important point, that at the end of the day, somebody needs to own it, right? And in this case, it's me, because I'm the longest serving member in my group, sort of by definition. And so a lot of the code that is written to, close to a deadline to get the experiments running gets written in a separate branch that later I will go in and incorporate it into the main branch, make sure that the pieces of that code that turned out to actually be good based on the experiments are the only ones that end up in the code, and that we don't end up with lots of sort of skeletons just left over from things that didn't work. Now, sometimes you do still end up with lots of skeletons in the code base, but at least having one person who knows that code base from the beginning and who takes some responsibility for keeping some consistency is useful.
Great, thanks. Thanks a lot.
Yes, so Daniel, go ahead, yeah.
Yeah, so I had some questions sort of about the software engineering side. So one question is, if you have 200,000 lines of code, how much of that do you think is currently sort of active versus, behind feature flags or on cold paths and so on?
That's a really good question. I wouldn't be able to give you an exact statistic, but all the code that is there listed is runnable, but not all of it is easily runnable. So some of it requires flags that are not documented, for example. that that we use just for benchmarking purposes. Some of it is actually debugging code. For example, code to just go and traverse some data structures and dump, run some tests over them to check their consistency, which is useful when you're doing algebraic transformations and you want to make sure you didn't break anything, things like that. So it's not all of it is code that runs if you just run the command line.
I was more broadly wondering about sort of how do you guys handle sort of the software engineering challenges? Do you do code reviews? How do you handle if you're using testing and you have like feature flags, you get some exponential growth in the number of possible flags you can set. Sort of how do you think about that?
So I would say for the most part, we don't too much. Generally there is this strategy of, at some point when I'm procrastinating about writing a sponsored report and I know I should be doing it, but I don't really want to, that's when I will go and sit down and just take the pieces of code from the latest branch that some students have experimented with and transfer them to the main code and take a little bit of care to make sure that features work well together, that we don't have mutually exclusive features, for example, where you can, even though it naturally might make sense to use the two together, you can't use the two of them together because it breaks. A big part of it is just a big set of tests. We have we have about 1,000 sketches at this point of various level of complexity that are used and run to make sure we don't break things when we're doing these sorts of things. But it's still, I wouldn't say by any stretch that this is production quality software.
Listening about you, it just always strikes me as funny about our community that, we're the formal reasoning community. When we build tools, what do? We ship a whole bunch of tests.
Yeah, that is absolutely true.
So Armando, it looks like you're the Linus of the sketch world then.
Sorry?
You're the Linus of the sketch world. Linus Torvalds. So you're the one who's the gatekeeper.
Yeah, more or less.
So great. I think, thanks a lot, Armando. This would be a long discussion if we let it go, but, I think we'll return to this topic at many future workshops. But thanks for starting this work up and keeping it going. That takes a lot of commitment and dedication in an academic setting, especially. So, really appreciate it.
Thanks.
Thank you.
Yeah. Of course, none of these would be possible without the actual students who do all the clever stuff and actually come up with the algorithms and do all the cool things here.
Yeah. Thanks. Yeah. So we'll move to the next speaker and the concluding speaker of the Verified Software workshop. So Ruzicka Piskac is a professor at Yale University. She's actually a student of someone who is on our Zoom meeting here, Victor Konchak. And so I remember meeting her as a student. She was quite exceptional in putting together very complex decision procedures and building systems based on these, and has really contributed quite a lot of significant work in the years since then. She'll be talking to us today about counterexample guided inference of modular specification. Ruzicka. So can you put it in full screen mode and start?
You're muted. Still muted.
Rosita, we can't hear you. Yeah.
So thank you very much for the kind introduction. And this talk will be about modular verification. And I also have to say, I'm a little bit nervous to give a talk in front of Victor. You know, like I knew that whenever I would be giving a talk, he would after this always be criticizing me. You didn't cover this, you didn't cover that. So let's see whether things have changed. You know, once a student, always a student. And so this talk will be a joint work with my student, Bill Hallahan and Ranjit Jhala. And let me actually start with what Ranjit raised the question, which was like the problem of modular verification. And you can see, I guess, do you all see a little Daphne code here in front of you? Am I sharing Daphne code?
Yeah, we see the Daphne code.
Thank you. So what is here, it's a very simple code. You can see what I'm doing is I'm trying to take a number. I'm trying to increase number 2 times. So I'm calling this functional increase. And I assume, you know, like it should be, this code should be verified because clearly there is no error in this code, right? I'm just increasing number twice and I'm invoking functional increase. So when I run this, you will see that I'm kind of get a comment, this doesn't hold. So, okay, I'm invoking this function increase. So let me actually delete, maybe the problem is function increase. Let me see whether I can verify increase, increment function. And this function is just adding number. Yes, I was able to verify that. So if you look, what was the main problem? I accidentally deleted instead of Control X. So the main problem was that although the function increment is correct, it's a specification. It's not strong enough. I mean, we are here just asking that the result should be greater than 0. So you can maybe say, you know, like, oh, she's now going all brave because Rustan is not on the call. She will be trashing Daphne. But actually, the problem that they have just shown is not really the problem that is problem of Daphne. Most modular verifiers will have a problem with this approach. I mean, recently I talked with Victor. He showed that stainless can solve this problem with a certain parameters, but formal verification of modular problem is the problem. It is a problem that we need to address. So let me now go with the slides and to put it in the full screen. So I said that I showed you the problem of that occurs in the Daphne best, but as our play tool, we will actually use Liquid Haskell and Haskell. So thank you very much, Ranjit, for a nice introduction to Liquid Haskell. So when I joined Yale, Paul Hudak was still alive, and you know that he was one of the main people in the Haskell community, and all of my students, they were always like, we want to work in Haskell. So this is how I actually ended up working in Haskell. And I just wanted to show this to revise the definition, right? So this is a Haskell code where we are having a map. Map takes 2 inputs. It takes a function and it takes a list and returns another list, and it's defined very simple. This function just is applied to every single element of the list. And now if you would use Liquid Haskell that Ranjit introduced, we could have this following spec, which will say size of the input list, which we will denote with XS, has to be the same as the size as the output list. So if we would give this to Liquid Haskell, it will be able to verify this. But if we go back to our old friend, this at 2, if Liquid Haskell is not able to verify that, this is the same like Daphne. And the reason is because when we have a modular verification, when you have a caller and callee, what has happened is once the callee is verified, the code is gone. I mean, the code is still there, but the modular verifiers don't look into that, but they're just focused on the specification. And then they use this spec so that they could actually verify the original function that is calling this function. To maybe show you a little bit more on the mean, clearly, if we would have both in the Daphne and the liquid Haskell stronger specification, the specification that would say that the return value has to be actually x plus 1, then we would be able to verify both in the Daphne and in liquid Haskell. So now let me go back to a little bit more complicated example. And this example takes as input a list of the list, and it returns this list flattened. So you have a list of the list, and our concat function will take all the lists and just make one list out of them. So if you look how it's inductively defined, it take on the empty list, it will just, you know, like do whatever, it will just, empty list will be empty list. If you have only one list, there's only one list. But if you have more than one list, if you have two lists, you will take first two lists, then you will apply append function, which actually just appends two lists together, and then you will recursively continue. So you would all agree this is a good definition. Somewhere externally, we have defined size and sum size, which would be exactly as you would assume. Size is the size of the list, sum size is sum of the all sizes that appear in the list. So now if we would like to verify this, we won't be able to verify for simple reason because app function does not have any specification. And now our goal is like, how would we be able to derive specification for app that would be strong enough that we can actually verify concat functions? So that will be our running example. And to our main goal in this work that I'm currently presenting is to automatically derive this required specification. And this work is still under development. It's not under submission, it's under development. Hopefully it will be under submission. So if you have any feedback, I would really glad to hear from you. And to go back when Shankar recalled when I first time visited, that was the standard. I mean, I did the same time back then. So, you know, like sometimes I'm brave, usually not, but sometimes I am. So now let me now go back to give you how we got actually motivated into working this into this area. So I had a student who was developing symbolic execution engine for Haskell. And then Ranjit approaches us like, hey, if you have symbolic execution engine for Haskell, I actually want to use that so that I can give some feedback to my students. And the course that I was teaching was, we have students who tried code and specification, and they would try to verify their code, right? The great thing was like, once if they succeed, they would be happy. But, you know, like we needed to have some sorts of feedback. And then we thought like, great, symbolic execution engine should be a great way to do that. But moment when we started to work in that area, we realized that, you know, like usually when your code is not working, you want to provide counterexample. But once you have a function that is calling another function, and they are both kind of one is verified and the other is kind of seems to be correct, what does it actually mean to provide counterexample? So this was in our work a couple of years back. We introduced the concept of abstract counterexamples in addition to standard counterexamples. And then we thought like, okay, that can help students to develop better understand where is their problem in their error. So I will define what are abstract counterexamples pretty soon. But once we kind of start to think, okay, this is the nice tool that can help students, then we actually started to big picture. So, you know, like when you are students try to understand where is the error in their code. But sometimes when you're writing a code that involves the other pieces of code, you actually don't want to just somehow say, oh, I want to pinpoint me where do I need to strengthen my spec. You actually write code so that you can automatically verify it. So what we then decided was like, let's take those examples, both versions that we derive, put them in the synthesizer and synthesize better and stronger specification. Like let's synthesize this x plus 1 by it automatically so that we can actually verify top level function. So now how this talk will be structured. First, I will introduce those types of counterexamples, and then I will tell you more about the whole tool as it is. And then, time permitting, I will also tell you a little bit more about linear integer arithmetic synthesizer that is deriving specification that then help us to verify the code. So let's start with a counterexample. One thing that when you talk about when people talk about counterexamples, usually they have counterexamples what we call usually counterexamples they have in mind are so-called concrete counterexamples. And let me give an example. So here is a standard map that you have seen initially. And if you look at here, what is the error, what we've done here, we accidentally forgot to put here that we should apply to the first element of the list, right? So there is something clearly, we have a wrong definition of the map, which means that our spec, which is that the sizes should be equal, will be violated. In this case, we do derive a concrete counterexample, which tells us, well, if you apply map on identity function and on the list containing only one, you will get 0. So we know that our function, our spec is violated, and actually we see indeed which concrete input will result in output that violates our spec. Now, when it comes to modular programs like the ones that we have seen initially, here is a little bit harder. What would actually be counterexample? So what we define in our PLDI paper as abstract counterexample, those are somehow more composite counterexamples, which says the following. Well, we provide first counterexample to increment, which we already did verify that is correct, and we say, well, if increment of 0 is 2, then when I apply to add 2 function to 0, we will result in the value 3. So I have input and output which are violated, and what we believe is a function that actually needs to be strengthened so that we will be able to verify that. So you can see that this is the way how we actually kind of pinpoint to students initially look into increment, because if you will manage to kind of get better results, then you will be able to prove maybe your add2 function. So now to give you a big picture how this whole tool is working, now that you understand what are concrete and abstract counterexample, let me actually start with our original friend, which is this flattening of the list, concat functions, which takes list of the lists and puts them all in the single list. How the big picture is going is like we are deriving those counterexamples independently whether they are concrete or abstract, and for each type of counterexamples, we will derive them as a system of constraints that our pre and post conditions will need to satisfy. So, you know, like practically each counterexample that we have will tell us, oh, you need to, you know, like this is what your pre and post will have to satisfy with this counterexample. So let's now start. When we try to verify concat, if we won't succeed simply because app doesn't have any spec, and you know, like anything goes, whatever you give as a input and output, you won't be able to verify as concat. So the first abstract counterexample that our tool, this is this G2 symbolic execution will return, will tell us, if app applied to empty list is the list that contains a 0 element, then we will get the following output in concat, which clearly will violate the spec. So we take this counterexample and we add it as our constraint that will be used in the synthesis. So we'll say, well, whenever 2 empty lists are satisfying our input, we're satisfying preconditions, then we know that 2 empty lists, which are input, and the list containing only 0 cannot actually be output. They are not satisfying. They cannot satisfy post condition. But now we already have something, right? We'll have app on the 2 empty lists. So let's actually see what is the real evaluation. So we do, you know, like our symbolic execution does 2 things. It actually unbinds in the same, like in lines, but also it derives this concrete and abstract counterexample. So when we evaluate app on the 2 empty lists, we actually get that this is an empty list. So this is another constraint that we will of course put. That's something that our app function should satisfy, saying like if preconditions hold on these 2 empty lists, then you know that output should be also empty list, and it should be our post condition. So now this is already some small number of constraints. Let's call the synthesizer, and synthesizer will produce some sorts of spec. I mean, you can already see, well, this cannot be right spec, but doesn't matter. It's still already some spec that can actually guide us. Maybe, you know, like maybe we will be able to get now, maybe we'll get some more better counterexamples. So we keep those constraints, but then if we try to verify our app function using this spec, we will immediately get not even abstract counterexample, but concrete counterexample, which will show us that clearly this spec that we have found, is not good spec for the apps. So we have now the spec which actually violates that the size of the output list should be 0. We take those two inputs and outputs and again put them in our system of constraints. And again, we run our tool, and I mean, sorry, when I say we run our tool, this loop is fully done automatically. User doesn't see all these guessings that are happening in the background. And we derive something as the size of X, size of output list is the size of one of the input lists. So this already looks somehow that we are getting somewhere, but you get what are we doing? We again call our tool again kind of tries to verify this. It will derive another set of concrete counterexamples and continues until we derive spec, which will tell us, look, size of the list C, which is a result of adding two lists together, is a size exactly the size of list X plus size of list Y. So as I said, again, all this is derived automatically, and then using this spec, we are able to verify original concat. So now I think I already revealed you majority of the basic ideas here that I've shown. So let me now tell you a little bit more about how the whole process works, right? We have now seen this concat an app, which is just one function invoking some other function. But if you would like to apply this to how our tool is working, it actually traverses the whole call graph. So you will assume that user will provide specification only for their top level function. And then we will go lower and to each levels before and try to derive a spec for each these functions below. So spoiler alerts, you know, like some of you will ask what is the biggest thing that you did? It's 37 functions that, you know, like that tool that invokes 37 functions. But now that you see, let me to see how it works. Like we start with the top level and we go lower and lower. Let me explain how would work how would be the ideal case, what would happen. So in ideal case, we start on the, you know, like we go through the level, we start at the top level, and once we are on the level I, so let's call it that we are now on the level F, where we want to synthesize spec for the F. What we will do, we will ignore everything, you know, like that is way below. We will just look at its intermediate levels, and we will repeat the process that you have just seen, right? So we will go and try to synthesize, strengthen the spec, make spec better, and so on. And once we derive the spec, which is, let's say, good enough for H, and good enough for G, and it was good enough that we are able to synthesize, that we are able to verify F, we go one step below and we repeat the process. Now, in an ideal case, we will come all the way to the leaf level, we will derive the spec for the last function, and then we will live happily ever after. However, okay, as you can imagine, it's not like that. Very often we will need to backtrack. And when we will need to backtrack is when we derive spec, when I say like it's good enough so that it kind of corresponds, that is good enough to verify correctness of let's say H, and it was strong enough that we verify F. But we could also find it was, you know, like that we might find counterexamples in the levels below. So when it is propagates higher, then we will actually have additional constraint added to our system of constraints, and we will have to repeat the process. Of course, since we are using a synthesis and we are deriving, you know, like you are deriving more and more system of more and more concrete values that are kind of telling you, oh, and your synthesis spec should satisfy this and satisfy that. Very often you can actually kind of go into the path that will then you will end up into the spec that is unrealizable. But the nice thing is that we are using our synthesizer is based on the SSMT solver. So if the spec is unrealizable, we will derive interpolant that will kind of prevent us to deriving exactly the same values And then this interpolant will be also part of the spec that will so that we can derive a new values that we need to explore. So, like it is a really high level picture. If someone would like to see all the details, please let me know. I will gladly send you the draft of the paper that we have. And in addition, when I said that those are that our abstract counterexamples are as simple as they are, we actually have those were counterexamples of a couple of years back. Later on in this work, we actually realized that counterexamples have several different, especially abstract counterexamples, ways, whether they're influencing preconditions, they're postconditions. So for each type of counterexample that our tool finds, we actually have a different set of constraints that we are putting there and so on. But the big picture is there. Run symbolic execution, find counterexamples based on the type of the counterexample, provide constraint, run the synthesis tool, and repeat the process until you're done. So now, Shankar, do I have time to go into a linear integer arithmetic or?
Sure, you have a couple of minutes, yeah.
Okay, so let me then just briefly outline the linear integer arithmetic synthesizer. So initially what we were trying, we were, Cesare and Andy Randalls can say we were pretty much bothering us, like because we bothering them because we were using lots of Saiga solvers. But then after we looked into type of constraints that we derived, we realized that actually many of them we could just solve by using directly by calling SMT solvers. So our synthesizer takes constraints that you have seen that we are deriving, and those but in addition, it's not only linear integer, like it's not only that you say if preconditions hold or this, then the post conditions have to hold or something else. It is also, you have seen there were measures, right? They're like some size, there were those externally defined functions. So all those things, if we try to give them to linear integer arithmetic solver, like then it's actually not really anymore only linear integer arithmetic. So what we actually had two, let's say, cute tricks that we used to take from linear integer arithmetic, convert it into only linear integer arithmetic, and then convert it back to the full features. That I already told you, either we will get the spec, or if it's unrealizable, we will get interpolant, which will prevent us from deriving the same type of numbers or whatever is our concrete values. So let me actually show how this conversion goes on this simple example. So what we have a function f that takes two integers and makes them a list, a very simple function. And now, how can integer linear and arithmetic constraints can occur? So you can maybe just put them like in this, there is one case that we can just put them like here. We can say, well, we take two integers, one is positive, one is negative, and it results in the list. Or the other will be with these measures that you have seen. Those are, I mean, I'm using measures, but those can be any functions that are actually using, that are resulting in linear integer arithmetic. So what the typical would be, for example, we will result in the list that has a size that is greater than 0. But then if you're talking about integers and lists and the data types, we can also put some constraints on the content of the data type. So what is here spec, the spec says like, well, this is the function that takes two integers and returns a list where every value is positive number. So how could we take all this, like applying functions to integers, functions hidden within data types? How can we actually apply this so that we come to the pure linear integer arithmetic? And those are two cases that I circled. Let me again show on the example. I mean, it's not that we only have several hacks. We indeed have all these algorithms fully formalized and described. So let me show the example. So let's assume that we derive some pre and post that has to, and the output is the list. So the pre says that it has to hold for 0, 1, and post has to hold for 0, 1, and then the output, which is 4, 5. Now, if we want to use size, we know that actually our input is not some parametric list, it's the concrete list of the 4 and 5. And we know that its size is actually value 2. So if our constraint will need to size, and that's decided based on the constraints that appear in the other spec, then we will actually put here, we will take this, we won't call this as the post of 0, 1 and the list calling 4, 5, but it will be of the size of, we will just put 2. So that means now let's assume we call our synthesizer and our synthesizer returns us value, which says like, okay, your last value has to be greater than 0. And then this is converted as the value which will say, okay, then your output is your post is actually that the output list has a size greater than 0. Similarly, we did it for the contents of the data structures. Like, for example, again, on the same example, we introduce additional predicate, which will be annotated with the contents, saying that this predicate talks only about the content. And then what we will get here will be additional constraints saying like, and you are talking only about 4, and we talk about 5, it has to satisfy. And again, calling our synthesizer maybe result like well, post, just like general post will say that the R has to be greater than 0. And then we remember this is about size. And the second one will tell us this R, which actually talks about content, has to be also greater than 2. I mean, clearly it could also be strictly greater than 3 or greater or equal than 4, but doesn't matter. So in this case, we can convert this again saying like the result is a list with the size greater than 0, and every element in the list has to be greater than 2. So now I told you already about something a little bit about evaluations. We ran that algorithm on the 15 benchmarks. Some of them were from a data set that Ranjit gave us. Some of them were from created by all of us. And then when we look into how it works, it turns out that we were able to synthesize a spec for almost all of them like within 3 minutes. And if you ask me how many functions invocations were there, they were usually like 3 to 6, something like that. But we were really proud, and we said we are not submitting or even considering submitting until we prove this k-means function, that this was the k-means function which actually had 34 functions when we would all involve when you would all enroll, and it was done slightly under 10 minutes. So to conclude, Ranjit started nicely to tell you that there are problems with modular verification. I tried to show you there are problems, but there are also synthesis is here to rescue. So let's let's make modular verification less scary. So I described this inference algorithm that automatically finds specification for the callee functions and then helps us to verify caller functions. We used SMT solver, and if you ask, someone asked me what is behind this synthesis, it is just like it's combination of template-based synthesis and synthesis by example. So it's like you get your constraints, you derive template, you instantiate, you call SMT solvers, you get parameters, and then you go back and convert it into into the spec. And I mean, that's it. So I would like to, I'm ready here to take questions. So thank you.
Thanks, Rosita. This is a really, I think, an important problem, and we often fall into the mistake of thinking that once we've given a pre-post condition for something, the problem is solved and we can move on. But we do have to come back to it and refine the specification for different users, and I think you need multiple contracts for the same piece of code.
Yes, exactly. Yeah.
So let's open it up for questions. Any? I think that we've already got some.
I can't see.
Lined up, Kedar.
Yes, thanks. Hi. So, Chazari, you can go on.
I misunderstood, so you go ahead.
Okay. All right. So yeah, I guess my question, this is interesting stuff. I guess my question was whether you have either a theorem or a hint of a theorem as to whether this iterative method is complete, or when it is complete.
We do. We actually do have. We have some requirements on the verifier and the synthesizer, and with respect to verifier and synthesizer, we have soundness and completeness theorems.
Okay, that's very cool.
I even have them somewhere here that I didn't present. So okay. Yeah. Okay. Sound verifier and counterexample, right? Yeah. Inference is sound. They say that. Okay, so I think this is not really for presenting, but like It's there still. It was kind of writing notes, but yes, we do have both soundness and completeness theorems about the approach.
Yeah.
And so, of course, it's kind of logic related, and also it has pretty reasonable requirements both on the verifier and the synthesizer and counterexample generator.
And is that for a particular logic of constraints, like some restricted logic of constraints?
So the whole approach is like general, right? If the verifier does this, which is like reasonable constraints, but then the synthesis approach that I showed, it's very particular to linear integer arithmetic. As I said, initially it didn't even cross our mind. We were just using CVC4 and their Zeiger solver based based on the examples. But Cesare, please cover your ears. It really took us sometimes often way too much time. And then we were looking like, wait, do we really need Zeiger solver, and can we just call it SMT solver? And that's the reasoning about linear integer arithmetic is still cheaper than Zeiger. So
Thanks.
Thank you.
Okay, Cesare, then Peter.
Yeah, so my point is always that one should use the right tool for the job. So
yeah, okay.
Well done. I would like to comment on the fact that this sort of work is, to follow up on what Shankar said, is actually really needed. I have some experience in the model checking of industrial models. Also because users don't have the patience to write contracts for all the subcomponents, and they will provide contracts for the top level components, and then that's about it. And then you need to somehow percolate all the system level contract all the way down. However, there is a meta level question I'd like to ask here. That is, when you're using a declarative pure language, like in your case you're using Haskell, versus say the language of Daphne. There's always the question of whether it is more efficient for any particular component to synthesize a contract versus simply inline the component or unfold it as recursive, right? And there's a lot of work that has been done, including by Victors and others, on unfolding functions, right? If you consider this, that sometimes it's just simply easier to inline instead of coming up with a contract.
In these examples that I've shown, many of the examples are actually, are recursive. So inlining there wouldn't really work.
Yes, but there are these unfolding approaches where you fold this a certain number of times, and then you reason inductively, right?
Yeah. So our G2 actually does use unfolding combined with symbolic evaluation. So it is somehow hidden in the tool that we are relying on, right? Yeah, but
and so you're finding that having the ability to synthesize contracts does improve what the system can prove overall.
Well, that's actually a good point. We didn't really do comparison, like let's just inline everything and to see whether you will be able to verify. This comparison we don't have. But,
no, this is not to criticize the work, because we definitely need this sort of stuff. That is the ability to synthesize contracts semi-automatically.
No, that we don't have.
But one also has, you find yourself having to balance this against the other approach.
It's that would be a good really comparison to see, but we don't have. But as I said, like I fully agree with you that one has to look into inlining, and that is that's about how our tool is actually, how do we call it originally, counterfactual symbolic execution, because you do in parallel, you inline stuff, and then you also do symbolic execution, and then you see, like you compare. So that's why
you do have the infrastructure to actually do this comparison. Yeah, it'd be interesting to see.
Yeah.
Thanks.
Sure, thank you.
Peter?
Yeah, I was going to ask the same question about inlining, but actually let me now comment. I think even if you have inlining, inferring a spec has many advantages, because you need to do the inference only once, and then when you change the program, of course, you don't need to re-verify the whole program as you would with inlining. So, you will still benefit from the modularity after this initial inference step. So I think this kind of work is very valuable. So great, thank you.
Yeah. We're doing similar work in model checking. So yeah, definitely.
Thank you.
By the way, summer school that I mentioned earlier, we had Tom Reps talking about a compositional analyzer which can do this kind of thing using interpolation. I would urge people to look at that work as well. He's working with Zach Kincaid on this. Okay, let's see. I think Victor has his hand up.
Hi, yeah. So I think most of it has been answered. Hi, Ranjit. Thanks for the talk. Indeed, our tool, for example, does only inlining, so to say, and user-provided contracts. And what we find is that sometimes if you have no specifications, then this K-induction is really too weak. And even specifications such as result is non-negative, right? My simplest example that comes to my mind is just size of a list. If you don't tell it that is non-negative and you're trying to assert is not equal to -5, it's just going to loop infinitely, right? And that's an example where this different enumerative synthesis, for example, over very simple templates will immediately get to something, right? So I find this really complementary in terms of what kind of specifications you can get to very quickly. So
I agree.
Yeah, so it's very exciting.
Chazri, you had a question?
No, sorry, I already asked my question. My bad.
Okay. So I think that brings us to the conclusion. Thanks, Rosita, for closing this off in style. So I'm going to switch off the recording at this point, and we can keep it on, continue the discussion for a little while after. Thanks, everyone.
Thank you.